We're a bit early, so we'll start at the time at 4 o'clock. I think we have still about like 4 minutes, 5 minutes or something. Hey, Justin.
Hi,
How are you
Nilesh.
doing?
Oh, how am I doing? Good. How are you?
Good, good, good. We are a bit early today, so we'll start at the time when it's 4. I guess I've seen people like signing on to Zoom 20 minutes in ahead of the class. They're hanging around here. Apparently, some of us do that, which is fine. I mean, nothing wrong with that, but I just look, I get anxious. I think that I'm late now because I get notifications that people are waiting for you. And so, okay. So
To be
sorry.
honest, Nilesh, I was probably one of those people, and it was just so that I was basically just hanging out and resting while, and
I see.
so I'd hear when you come on. That would turn me back to the computer.
Okay.
Did you get snow at your place?
Yes, it is all snow outside, and I did go out a walk on a long walk with the dog in the snow, and it is beautiful.
Is it cold?
Yeah, the temperature is like close to 0 as in centigrade, but you can call it cold. But I thought you live here, and so you from Alaska, right? So you
No, my
cold.
in-laws are from Fairbanks, so
Right. So you shouldn't even bother about what cold is. I mean,
you know, honestly though,
Uh-huh.
the wet cold here feels colder than -20 up in Fairbanks.
I guess that is true because I agree. You know, the thing that I like about Fairbanks is that it doesn't get wet, and so there is beauty. You can just walk around anytime as long as you're properly clothed. You know, and you know, layer and layers of clothing. It's totally fine.
Yeah, and it's you know, and it's also you get different gear, but down here you know, you get 30 degrees with that wet humidity, just freezes you to the bone.
Yeah, yeah. So give me a second. I just close the doors because there are people who might make some noise. So they are in my home. Hold on. Look at the doors. There we go. So the door is taken care of.
Don't forget your mic.
And I will grab the mic again. But before that, I want to adjust some lighting. Not that you care about it, but I just want to make sure that the lights are on. I don't think you want to look at my face, but at least I feel that you may want to. So I just put lights on. And hey, John. I see John. I see. Actually, oh man, there are 10 people already. Okay. So I think it is 4 o'clock. Okay, let's go start. Let's get started. Okay, there is my microphone in place. My pen should be functional. Yes, it is. My notability should bring up. My handwriting should be ready and also visible. So it should be coming up. There we go. So you should see my handwriting. You should see my face, and my audio should be clear. With that, we begin. So we'll begin with a comment. A couple of you have successfully set up this thing called pi.hole, which is amazing to note that you just pick up an idea and implement, and that's beautiful. I mean, that is amazing that you actually like what I just casually mentioned. You go and implement it, which is awesome. It means that you like it. That's a good sign. If you do not know what Pi.hole was, when I talked about it briefly the last time, it is this application Pi.hole, which is what
at least 3 of you have already implemented, which is beautiful. It has helped me reduce about 9% of trash in my internet. So that's the product that is available on GitHub. Pi.hole is the internal name. The name outside is Pi-hole. Pi-hole is the actual name of the product in this website, and it's on GitHub and all that. So today we talk about this thing called Kubernetes, and that's the plan. And so it's loading up. That's the product that I want to talk about. And we want to do exercises on this, and we'll also follow along the hard way of doing things. There is an easy way. So I'll maybe demonstrate the easy way also. But the more important detail behind this is the hard way. The hard way of doing things, which is this way. And this really gives you complete understanding. You then, once you go through this motions of this exercise, which is basically hands-on exercise, you will understand what Kubernetes is, and you can implement it in your own location, in your what I call at the smallest situations. You can implement it in a bunch of Raspberry Pis. Raspberry Pi cluster Kubernetes. That is also possible. Technically, it works out. You can see how this gentleman actually specializes in creating Raspberry Pi-based clusters. And he runs Kubernetes on that, which is more like a hobby. And so the real implementation of Kubernetes happens in either your own data center with a bunch of real hardware lying around that you might have in your company, or you find that there is a whole range of things, like, for example, in the implementation. One more thing, I think this certificate thing. So what happened is they generated architecture certificates too early and did not generate the DevOps certificate until this morning. So this morning, your older incorrectly issued architecture certificates have been retracted. That's what I understand. And you have an email from the college that shows that this DevOps certificate is now available for download. So please download the correct one from this website, the college website, and then submit that one to the LTP program. For those of you who are Boeing employees, please follow along and submit it to the LTP website, the DevOps one, the correct one. That's what you should do. And then later on whenever that March 9th, that date, we will finish the architecture segment. Also, at that time, you will also receive another email saying that the revised cloud architecture certificates will be available at some point, like after March 9th, maybe a couple of days after that. And at that time, you will take that certificate, not the one that you may have before, and you may have preserved a copy. Ignore that, keep it with you, but just ignore it. Don't do nothing with it. Wait for the March 9th date. And after that, you will receive another email that will advise you about architecture certificate. Use that piece of paper from the college website and use that to submit to LTP. That should take care of it. DevOps, you can submit it as today because it should be available to you. Architecture, wait for it until the course finishes. If you submit it today, you will run into issues, or somebody will question something. So don't do that, basically. Okay, that's about the certificates. So we'll resume what we were discussing, which is this thing. And some of us discussed the last time that somebody is debating whether Kubernetes is slow or good or fast or bad or whatever. I'll let you guys and those guys make that decision whether it is good for you or not. I'm not making that judgment because that's not the point in here. So that's the focus, is not actually go debate a particular topic, but understand what this thing is. Maybe it is useful, maybe it is not. Who knows? We'll find out. So let's understand what this thing is. So this origins of this thing came from a research paper. The research paper is called the Borg research paper, Borg paper. So if you search for the Borg paper word, that is what you will find out, this link. And I'll grab that link for you and paste it in Slack chat right there. And we will probably expect 2 guests today who will just show up. And so I think I need to send them a notice that they can join. So that I think I forgot about that completely. So they might show up in the program at sometime like 5:30 or so. And I'm just sending them a way to join this. They want to just see how it's going on. So that's what I'm expecting. These guys to show up. These 2 guys are likely to join at about 5 o'clock. They'll come, listen, maybe not talk at all and go away. Who knows? We'll let them participate. But the thing that I want to give you guys is a link to this Borg paper. This product is the idea that is implemented in Google's enterprise, in the company inside, which is what they have been doing for the last 10, 15 years. This is how they manage their internal operations, in their internal company things. Whatever they do, everything in Google today runs in containers. And that is this system called Borg, B-O-R-G, is the foundation. What they have been built, they have built in for the last 10 to 15 years. And they have finally written down a paper about how they do things internally. This is a research paper, and you can read a PDF file right there. This is published and publicly available. And if you scroll straight to the bottom and read the conclusion, that's what I want to focus today on, is not reading the paper because it's fairly elaborate. So I'll let you read the paper later on, but let's focus on the conclusion. The conclusion is right here. It reads like this: virtually all of Google's cluster workloads have switched to using Borg over the past decade. We continue to evolve it and have applied the lessons that we have learned from it to Kubernetes. So effectively speaking, this product that we are discussing today is actually an evolution of the Borg system, which is the foundation of how Google manages its internal operations. And that is this product available here on GitHub. It is open, meaning it is, let's read the license. Let's begin that. So let's go GitHub and look at Kubernetes. Not this, Kubernetes, and that product. That product is, we have 11,600 forks. We have 32,000 stars and 2,000 watches, and 1,600 contributors, 344 releases. The latest version available is coming up 11 alpha, 11, 10 alpha, 10 beta. But I think the 10.193 is the stable release right there, this one. 192 is what I have running in CloudGenius. So slightly older. This is the latest stable. Let's go see the date for this latest stable, 193. The date turns out to be 21 days ago. So that's how recent it is. That is available and in open domain, so people can just consume it. The license that is this thing made available is in the Apache license, which is a fairly liberal license. So you can just use it wherever you feel like. So most companies will accept Apache licenses in their corporations comfortably. Having said this idea, what is this? What does this do for us? It is actually a collection of best practices that Google has started with, and now it has been taken over. It's not controlled by Google anymore. It is controlled by the CNCF, which is the body known as Cloud Native Computing Foundation. This is the body which actually is. Let's adjust this a little bit. If you look at the members in that body, this body comprises of, by the way, your Boeing company has Cloud Foundry, which is also a part of the same, I think. So you can see all the projects in that foundation. And if you look up all the projects, you will find that one of the projects is your Cloud Foundry. There are lots of projects that are currently incubating. Kubernetes, Prometheus, OpenTracing, Fluentd, gRPC, Containerd, Rocket, CNI, and the list goes on. And some of the newer ones coming up. the company that are behind this, the member companies are big people. Like you can see the list here. Interestingly, you find that even I think, was it Microsoft or somebody Microsoft joined Linux Foundation, not this foundation. Microsoft actually joined Linux Foundation, which is another crazy move. But it has happened. I never imagined it would happen, but probably 3 years ago, I started to get a feel that they might actually go in that direction. So these are the companies behind that foundation we are looking at, which is CNCF, Cloud Native Compute Foundation. So we have big people, Alibaba, AWS, and all, even Azure. There we go. So we have, I thought it was there. So Azure is a part of CNCF and all other companies, including Google themselves, which are not listed here. Amazing. Oh, there is Google Cloud, there is Azure Cloud, AWS Cloud, Pivotal listed, Red Hat listed. So all these companies, most of them, almost every one of them has their own implementation, which is conformant to the Kubernetes ways of doing things. And they have a service that runs Kubernetes. What does that translate to? You can run this thing on your own hardware. And on the other extreme, you can run this as a ready solution. Ready solution available. So you just go to Amazon, actually not Amazon yet, not yet, but they're coming up with this EKS. You can go to Amazon, Azure, and make use of AKS, Azure Kubernetes Service. You can go to Google Cloud and use the Google Kubernetes engine. You can go to Alibaba Cloud, and they have something like that, pretty similar. I don't know the names, but like this, you can see all the member companies, like here, they will provide you a ready to use, ready to consume Kubernetes solution, which is the easy way. The easy way is as simple as, I mean, you will find it amusing, but it's as simple as starting a machine in the cloud. Similarly, you can just go to, say, this example. I'm going to Google Cloud as an example, and I'll just go to the console, and then I select one of the projects that I have there, like this in the lab project that I have right there. And here I say, you know what, please give me a Kubernetes cluster. So I'll say Kubernetes cluster, and engine is getting ready. Take a minute or two. So that will take up. This is a new project that I just created for our use in the program. So that's why it is not ready yet. Maybe I can switch to a different project, like the staging area. That should be ready already. So here I can just quickly create a cluster. And here I can say that I want to name this the Cloud Genius cluster. And I will like to have it in any of these areas, in any of these regional locations. So my preference is, what's my preference? What should be my preference, actually? My preference should be where my customers are. So if I happen to create a new solution for the India region, I should actually select something like here, one of those guys. So South 1B, that should be the preference if I am going to target India, for example. And Asia South 1B or 1A, one of those guys, 1A, 1C, whatever, and select the version number. So I have 192. There we go. I can select how many compute nodes I want. I can maybe get 2 or maybe more. So I can select how many I want. And then I can choose which operating system do I load up those machines with. Now here there are only 2 choices, which is strange. You get either Ubuntu choice, or you get another choice called COS. Only 2 choices. Because actually, practically speaking, these choices have actually nothing to do with your day-to-day operations, because you don't even connect to that operating system at all. This is just the underlying thing that happens to run on the machines that you're getting. So I decide to get 2 CPU machines and 3 of them, or maybe 10 of them, and maybe more. And so that, sorry, what did I say? Number 10 of them. And then here, I don't even actually connect directly to those 10 machines, because that is not how we operate when we are operating containers. Because we don't attempt to even bother. We don't have a key placed in that location. We don't need to, because we are just dealing with containers and containers alone. So we don't even care which operating system here it is, whether it's Ubuntu or Core, or this, not Core OS, but this is a Google customized operating system, which is Linux based, but it is updated a lot more quicker than this. So I prefer the container optimized OS because I suspect that Google might update any issue faster, and it's their own operating system, so I just use theirs. That's my current preference, but of course I get to choose, so I have the choice. I can then go ahead and enable certain other options and click the create button. That's pretty much it. I get the ready-made cluster in like 5 to 10 minutes. That's all it takes to create a cluster. And it's already configured and connected to my laptop, and all that good stuff will automatically happen. What I want to do is not do the easy way today. So we will understand what it is. We'll also play with the easy method, and I'll guide you in terms of how you can further optimize, and maybe somewhere in between this extreme and that extreme, we'll find intermediate ways in which we can maybe make our life easy and run it on, let's say, 3 to 10 machines or something like that. And we will use Terraform as a deployment tool to create something in between, not all the way on our own hardware, not all the way in a simple ready to use solution, but something in between we can customize and construct whatever exactly fits our business requirement. We can go that direction also. It's like a range here. Super easy and super hard, and somewhere in between. That somewhere in between aspect, this slider, you can move it around either way you like. That comes at various price points. And actually that also comes at a various performance points and other feature sets. And so it's not as simple as this is cheaper versus easier. That's not the idea. It can also be expensive. In fact, the pricing depends on how many machines you deploy, whether it is 3 or 10 or 100 or more. So that, and the size of the machines also. So that's what actually drives the pricing. If you're doing it the hard way, on your own hardware, in a lab or in your data center, that's a different story versus doing it easy way. But let's go under the covers and exactly what does it do for us. So I have a cluster already running, as I already told you. So let's go inspect that cluster right now. And let's see who, I think I see lots of people just joined in, apparently. Let's see who just joined in. It's just us, no visitors as yet. I'm just expecting 2 visitors today. So they might pop up, but they will tell us when they come, they'll announce themselves. So the idea here is I want to actually visit a small Kubernetes cluster I have running to inspect what it contains. And then we'll go through its components, its ingredients that constitute a cluster. So I'll show you a very, very simple cluster right now, which is already running in a different project. So I'll go to the production project, which is where I have currently a very small cluster running right there. This cluster, as you can see, is running in US West 1A, which is probably somewhere in California or maybe Oregon, I don't know, probably Oregon. It has 2 machines with a custom CPU type. So there are 4 CPUs and 15 GB memory. So this is, I think, the size is in 1 standard 2. I think that's the size. I'm not sure, but let's confirm that. So that's the Google's way of sizing a machine type. You can see what sizes are available. And so the sizes I think I have chosen is N1 standard 2, which gives me 2 CPUs per machine and 7.5 gigs of RAM and some disk and some total capacity possible on a disk. So that's the limits of this type, machine type N1 standard 2. That's the that's the T2 micro, N3 medium type concept. In Amazon, you will find T2 micro, the smallest, and then further other sizes like M3 large, M4 large, and other bigger sizes. Same concept here, except there is something new and different with Google Cloud that I want you to be aware of, which is unique to them. And I think it is interesting, and therefore I mention it. It is interesting in that if you go to just get a machine in Google's compute engine, you go to VM instances, In here, you can choose to create an instance of the size that they give you, a ready-made size. So you can select that I would like to get 1 CPU, or you can get a micro size, like less than 1 CPU, or a small size. It's only 1 CPU, but very small memory. So 1.7 GB memory, 0.6 memory, so F1 small, G1 small, 2 sizes available. These are more of a experimental situation. For a proper production usage, you will begin at the 1 CPU, 3.75 GB memory, or 2 CPU, 7.5 GB memory. That's the sizes available. However, these are not the only sizes that you are limited to. In fact, in Google, you can customize. And you can pick and choose how much CPU and how much memory you want, even extended memory that you might want. So let me adjust this a little bit so I can show you properly. Come on. This is not, okay, well, let me go full screen. So full screen and adjust the font. Actual size. There we go. And here we should be able to select a somewhat reasonable, like 32 CPU and extended memory if I want. And then I can also choose the CPU platform if I want Skylake or Broadwell, or which CPU family do I need on the machine itself. So you can go the newer version, Skylake. You can also customize and add the number of GPUs are not available in the zone you selected. So you have to change to a different zone in GPU. That is something that maybe one central will have it. So here you can say that I would like to get 8 GPUs with NVIDIA Tesla, K80 included in the machine types. And that's the kind of customization. So it's fine-grained customization. You can select how many CPUs you want, how much exact amount of memory you would like to have, and extended memory if you want to have those machines, and it will be priced accordingly. In fact, you can see that the pricing calculator right there automatically gives you some estimates on how much will they be charging you on an hourly basis, depending on your choice of number of cores and number of memory. And it's fairly fine-grained collection. So you don't even have to go through this basic limited listing, like right there. You have N1 standard 1, N1 standard 2, like that, and then more types available. But this is not the only selection you get. You can go crazy and customize it with a very, very small number of CPU, like 2 CPUs maybe, and a very large amount of RAM, like that. Or the other way, you can shrink. If your CPU intense application, you can go large number of CPU and a very low amount of RAM. So let's say, yeah, this 78 CPUs, and my RAM requirement is only so much. So I can save some money there. I mean, maybe in this situation, I'm hourly spending about $2.10, and I'm able to get 78 CPU, virtual CPU, or any number that I prefer here, and a small amount of memory, comparatively speaking. I can adjust what I want depending on the application characteristics that I have in my hand. And so now you saw me do something, like I was able to tweak the CPU count, the memory size. So I'm able to size whatever I want. I'm able to size my memory whatever I want. And what I would like to do is construct a definition of machine type. I'll call it my type, or rather the classification for application type A, and for another one for application type B. I can construct another such metric. More CPU, so more of CPU, less of memory, and like that. Here I have less of CPU and more of memory. I can customize and tweak whatever I want depending on the application type. And what I just did is the first concept which I wanted to talk about, which is what I'm doing is creating these templates for machine types. And I'll construct what I call node pool. A node pool is a collection of machines that will be inside your Kubernetes cluster and will be appropriate to run this type of application versus that type of application. If you have a low CPU, high memory, so this is the low indicator, this is the high indicator. If you're low CPU, high memory requirement, of that type, then for this application, you will select a machine from this pool as opposed to that pool. So if you have other type of application which requires more CPU and less memory, you will select a machine from this pool. And so those two pools are distinctly different from each other. You can have pools of multiple different types aggregate together in one Kubernetes cluster. That's a possibility. It is unique, I think, currently to Google Cloud, where you can actually tweak. If you go to Amazon, not Amazon ready yet. Amazon is not ready yet, but Azure is. Azure AKS should be there. Why the searches are not coming up? Come on, Azure AKS. There it is. So here, they don't have this concept of node pool quite yet. They have this service available. This is not the right service. Hosted Kubernetes. Yeah, this is it. Yeah. So if you go here, they don't have a concept of node pool like I just described, like this. Different types of machines, the other types of machines, all you get is just one type. They're evolving slowly, and they will have this type of method also available. But under the hood, there will be some machines like that you will put together in a cluster. And the underlying concept is very similar to the other cluster we saw, which was a Docker Swarm. In Docker Swarm, you remember we had one manager and two workers, and we were able to construct them together and put a swarm around it. We'll do some more exercises with Swarm also, and also with Kubernetes, with actual application deployments and putting the end-to-end game. We'll do those also. But for right now, just getting the framework of understanding this clustering thing and getting them to be up and running for us in a variety of situations, all the way, the easy way, the hard way, both ways. And so in here, you remember that this guy, when you say you become a manager, it will spit out a token. And then you give that token to these guys, and then they ask to join them. That concept here of producing a token and giving it to the other guys and then asking the other guys to join is similar here. You have machines of various types. You allocate some of them as your manager machines and the other ones as worker machines. And then you do the same thing, pretty similar in structure. So there is a thing called token, and you give it to these guys, and they will just join the cluster. That's how it rolls. The same idea again, but the concept here is slightly different. It is the Google's collection of best practices as opposed to other people's collection of best practices. So this is the Docker company behind it. This is the Google company, used to be behind Kubernetes cluster, but now it is the Cloud Native Compute Foundation. Those people together behind. And I think even Docker joined them, if I remember right. I think Docker is now using Kubernetes, if I understand it right. Docker uses...
It was on the picture. It was right on the picture.
Sorry?
It was on the picture, on the
Was
previous
it there somewhere?
left-hand side.
Oh, there it is. Right. Docker uses Kubernetes. Yes, thank you. Yeah, I just don't know why I'm not able to detect these these graphical references. So Docker uses Kubernetes right there. So docker.com/Kubernetes, and they are now, Docker is now powered by Swarm and Kubernetes. So they're doing both. I mean, it's a good thing that they're adopting. So basically, the best platform that you want will win. Eventually. I mean, who cares about winning and losing? It's just there. It's for you to use. You pick and choose. You play with both. If you like one of them, you use them. Otherwise, you don't like any of them, you use something else. There's no in open source, there's no winning or losing, right? That people in the press talk about these things all the time. So sometimes I even accidentally throw a word winning. It has no meaning to it. And there's nobody winning. Only you and I are the winners. So bottom line, we are able to construct node pools, and it's a collection of machines that behave differently from other machines like this type. More memory, less RAM, less memory, more RAM, different node pool. You can then put them in a cluster like this and then configure something functional. Another concept that I want to talk about before we jump into an exercise to build our own cluster to understand other components as we go along is this idea that I will like to show you. Back to my Kubernetes running cluster. As you can see, it has 4 CPUs total, 15 GB memory. So under the hood, there are 2 machines, 2 cluster sizes 2. It's a very small setup. If I go in there, detail, and inspect, you will see what I have is the version of Kubernetes in the master. This is the master machine running, and the version is 192. If you now scroll down, I have a node pool. In my node pool, I call it the default pool. There are only 2 machines in the worker zone, in the worker area, in the pools. They are also running the same version of 192. The operating system that I'm using is COS, which is not Ubuntu. There are only 2 choices. The machine types I'm using for the workers are N1 standard 2. Total core 4 and 15 GB and all that. But what else do I have? Do I have some add-ons? Yes, I have 2 add-ons. They are Kubernetes dashboard and a load balancer. So I'm using these 2 extra services on top in that cluster of 2 machines. Now let us see what I have here in terms of the master version. Now you will notice that in here, the master, when you're using a ready to use easy option of a ready solution, most of these companies like Google, Amazon, Azure, and others will charge you only for the worker. So I have 1 worker here. So sorry, 2 workers, 0 and 1. So I pay only for that. Of course, there's a need for a manager, and another manager. So typically you will have 3 managers, or sometimes more on a very, very big cluster. And the good thing about using the easy route is you don't have to pay for these guys. So it's 0. You just have to pay for these machines. And so that's the bill. That's the usage model I'm describing, because it is competitive pressure that you see that, these machines, they are eating the cost. The cloud companies like Google and Azure, both of them are eating the cost of these machines. They're just giving you a service so that you can decide what version of Kubernetes you want for the manager nodes to run. You don't even get to touch them. All you just get is a managed control that controls the node pool that you have here. That's what you really want. Your work happens to be running here on the workers, so that's what you pay for. And you don't have to pay for these, but you just control the version number you want to use, and so they give you a set of versions available. Like you saw in this example, I get to choose what version I have. So when I say I would like to create a new cluster, I can simply select the version I have. These are the choices available. You don't get all the choices, but I just happen to have chosen this choice. And you can choose any choice that's a currently available choice. It is a limited set compared to what you will see otherwise in GitHub. If you go to GitHub and find, there are lots of versions available, including beta versions and alpha versions and all that, which may not be relevant for production usage. So they limit it to only these versions. And eventually this will update to 193 someday. And when that does, they will update and help me update the management layer, which I don't have to worry about. All I worry about is whether my applications are running in containers, and I just schedule them to run on these 2 machines. And I don't even dictate whether it runs on this box or this box. I don't need to, because Kubernetes has another thing. The second important thing here is called a scheduler. So you understand the concept of node pools, a collection of machines. Now the idea of a scheduler. So so the scheduler actually runs in here in the masters, in the master node on the service side. So either you run the masters yourself, or you use a ready to consume service, in which case you don't have to pay for the master. But that's where the masters actually run a service. It's called a scheduler, which will take your applications containerized and then decide which is the best node pool, and among those node pools, which is the best spot at the machine level, whether it is W0 or W1, or maybe more, depending on how many machines and how many node pools you have, which is the right node pool and which is the right machine for this particular container to run. That's what the scheduler does, which is that's one of the best practices that these guys have eventually codified in form of Kubernetes, which comes from Borg system, which is what they're claiming here. Is builds upon 15 years of experience of running production workloads at Google and all that. So that's what we know and that we're dealing with. So there is a scheduler that will take your work and deploy it on the nodes, like right there. The node is what these machines are known as. These are nodes. W0, W1 are nodes. The collection is called a pool, and you just put some workload in form of applications running in containers, and you just talk to the manager. Hey, can I please have you run the load on the appropriate machines that you figure out where you want to run? The scheduler will run it for you. That's the second concept. The next concept here is that we have to understand how do we put our applications in a meaningful fashion together. For example, if you have WordPress application, and you remember and recall from our previous exercises that we had this thing called a database to go along with it. So typically this database and the WordPress application itself, and they are what I will then put them together. If this is a separate container, this is another container, but I would like to put them together, right? And that is my desire. So in case of Kubernetes, they have this concept called a pod. A pod is like Peapod. And a container that we know of already is the P in the pod. So you have in this example, a pod showing you this and this, two containers together. So it will be managed collectively in form of one pod that takes care of this application, which constitutes a database also. So it's a separate container, but they all go together. So it's easier for us to look at a bigger picture, multiple applications running, and you just construct and define a pod, and you then talk to the management machines. Say, hey, would you please run this pod for us? Or even better, actually you just define how the pod should look like, and you actually create what is known as a deployment. So there is a concept of deployment, which you define how you want the pod to run, and you define that deployment in form of another YAML file. And you say, hey, take my YAML deployment and just deploy it. So it will include definition of the pod itself, which includes the definition of these two containers. And that's how you will construct a YAML file that will call a deployment. So now let us go look at an example YAML file. Let's see if we can find a quick example. It's very easy to understand once you have gone through the idea of a container and run applications inside there. You already know what these YAML files look like. So I'll just show you an example YAML file right now to get you the idea or wrap your head around the idea of a deployment. So I'm just trying to find where my actual examples are. And let's see. Okay. So I am trying to find out where that thing I have placed. So I think it is called GKE. Yes. So in there, if I open my Atom editor and see if I can bring up the right deployment file.
Can you increase the resolution a bit?
I will. It is. I have to actually open the file to increase the resolution. This is currently the folder view. So here is an example deployment. I'll just pick up a simplest one. Maybe this is a good one. Now I'll increase the resolution. So here, this is a classic deployment of application called that you're familiar with is line number 19. That is a container deployed. Now let's go examine the details behind it. In here, there is this segment called containers, which contains only one container right now. That's the portion. In fact, line number 22 all the way down, this portion is kind of comments. So I'm going to remove them for simplicity. And even this one can be removed. And on the very top, that one can also be removed. So I'll go make bigger font. So now let's go see this structurally. What we have is we are defining a type called deployment. We're giving it some name, TCS. That's the name I chose across the board. So you'll see several occurrences of the same name. But then I'm asking for how many replicas I want. So I'm saying one replica. I have a selector defined as to how do I actually detect the presence of this particular runtime pod that I'm defining as a deployment. So these segments are a template definition, and this segment is a selector definition. Above that, we have a replica, and the actual specification is simply these lines. Actually, there's only one container in here. That is it. So you specify an image, which is basically Cloud Genius's WordPress image. That image is in line number 16. If the image is not available in the Kubernetes cluster, you pull it. You say Docker pull image ID. So it gets pulled. I'm assigning it a name in line number 18. And then I'm defining a volume mount point, volume mount. And then there is another reference to volumes, which is line 22 and down. Well, so this is a new concept that I did not discuss yet, but I would like to describe that also to you. That is a necessary thing to talk about, because if you remember this discussion here, WP and DB, there was another thing, which is where you store the data. And that data needs to be stored not in here, not in containers, but somewhere outside, safe, in a persistent storage. And that is the next idea I would like to talk about now. So up until now, we have discussed the idea of a deployment, which defines like a YAML file in this example that you looked at. And the other idea that is critical to understand these details is the idea of a volume and a volume mount. So what is a volume? Volume is typically a place to store stuff. It is storage. Now, if on the two extremes, like I mentioned, the hard way and the simple way, the easy way, the choices of storage available can be iSCSI, or some kind of a network attached storage solution, or some other solution, maybe fiber channel, who knows, whatever you might have in your company. That's the hard way storage available in your NAS, in your SAN, those types. That's the choice available in storage. In the easy side, if you're on the Amazon Web Services, which is not ready yet, you will eventually have this thing called, what's it called? Elastic File System, EFS, which is basically NFS. That's what this is. So you get NFS solution in the cloud. If you are on Azure's cloud, you get, what is it called? SMB. What's the name they use? The name they use is called Azure Files. This is basically SMB implementation, Samba. If you are on Google Cloud, you don't have NFS yet, but eventually it will come. Until that time, what you do have in Google Cloud is persistent disk. So this PD, as Google calls it, PD, is basically block storage. And you can get block storage in this cloud also. They have a different name for it, and I'm forgetting what the name they use. Basically, it is block storage, block. So you basically get a disk, persistent disk type structure in Azure Cloud. And you also have the Elastic Block Storage, EBS volume, in Amazon's cloud. So those storage options are available on the easy and the hard side, both sides. But what Kubernetes does is simplifies all of these things and make it very, very simple. What you do in a given deployment is that you define that I have some volumes. And then I will have volume claims. So you can begin defining that I have this NFS mount point. And in there, I have, say, /mnt/ some folder number 1, folder number 2, like that. Multiple folders that I will then use eventually. So I know that they are accessible currently by NFS. So I would like to have these 3 different volumes made available to 3 different, or maybe more than 3 different, or maybe less than 3 different applications that I have deployed. So there is this application 1, there is application number 2, and there could be application 3 and 4, but these guys need some storage. So I can then have this application claim that storage, and this application claim that storage, and this application can claim that storage, and it can be shared, read, write, many, but it can be read, write by one, or read only types of relationships in the claim. Depending on what my business logic is, you can decide whether my application 4 gets read-only access to this particular volume or not. It's really up to you as to what you decide, whether you want read write by many, read write by one, or read write by, or read only by everybody. So that permission structure of a volume versus a volume claim is the idea that is in Kubernetes, which is, I think, a more elegant approach to dealing with storage as such. Because what you're doing is providing a layer of abstraction and hiding all this detail, whether it's iSCSI, NAS, Fiber Channel, or maybe just a disk on a SAN, or anything else that you might have in your real enterprise storage in your data center. Versus on the other hand, in variety of clouds, you have NFS, EFS, SMB, and God knows how many varieties might come up in the future. Maybe there is another thing called Gluster FS, which you can implement in the cloud as well as here. You can run Gluster FS, which is a highly reliable, highly available storage solution that is open source, by the way. And so if you look at Gluster, if you do not know, Gluster FS is this product which is, I think, phenomenal. I mean, no doubt about the quality, reliability, and availability, and all the utilities that you can think of about this. Making that storage is a scalable network file system, and you can put the underlying disks on multiple machines across multiple locations. And this is now owned by Red Hat, if I remember right. And at the bottom, you can see it is by Red Hat. So they bought it. They bought the team, actually, and they're now part of Red Hat company. You can install Gluster, and we will have an exercise on this as to how do you do this? How do you do enterprise-grade storage solution? So we will have this exercise at a later time, but for right now, I'm just pasting you a link. So the link is right there. Now back in here. What I'm talking about is volumes versus volume claims. The idea is you're abstracting the references to volumes and hiding all this detail, whether it's Gluster or SAN or whatever else or other types, but just referencing them by the friendly name that Kubernetes will like to use as a volume reference, like this. Let's go see an example right there. In here, you will see that I'm specifying a volume in line number 22 and down. I'm saying that I am going to use the volume right there. In line number 23, I specify a name, and it is a claim. This is a claim by this application on another volume. The claim is called out in line number 24. That is a persistent volume claim that this application running in this container needs some storage. So please give it to me. I'm claiming that storage. Now, corresponding to this claim, there has to be a volume provided to this container, for which we need to have some volume created. So if you can go to the PV section right here, which is where I have written it down, we'll find that there is this volume creation called out, where I'm actually creating several volumes. Hold on, let's read this carefully. Yes. So you will find that on the right half of the screen, there is both a volume and a volume claim. Line number 1 through 13 is the volume definition, and lines below that is the claim definition. So you can see where I'm defining a volume and defining a claim, and then using that in a real deployment, which is on the left side, line number 23. I'm calling that volume by name. So let's go see the upper portions in the right side where I'm defining a volume. What I'm saying here is in line 1 through 13 is that I am going to use, or rather define, a 20 gigabyte storage space as read write many. 20 gig storage space as read write many, by many containers can concurrently read and write to that storage. This is on the path /TCS. I mean, that's a file folder name that I'm having here, defined here. So instead of F1, it will be /TCS. And it'll be mounted in some location like that. So that's the name I want to use and assign it to this container called TCS. That's the reference you're looking at. This is the application, which is the WordPress application that you saw in the example. It is mapping to this folder somewhere in some NAS. And that NAS also is created inside the same cluster. So we'll see that. But here, I think this is fixed already. So this fix me is a comment that need not be there. Now, this server that runs our NFS solution is another deployment, by the way. So you can see that deployment here. In the left down section, you will find that there is a NFS server deployed and created. Let's go read that. It's going to be small a little bit, so I'll adjust the font just a minute. Font adjustment. And maybe remove some of the commentary to make it a little bigger. There we go. So here on the bottom left side, I'm defining an NFS server as a deployment. So here's the deployment running NFS server itself. This is the only one server running in a container that defines my NFS server for the entire cluster. What it does is actually mounts a disk available in that cloud, which is this disk right there, line number 34. There is a disk created in that cloud, in the Google Cloud, where I actually grab that disk by its name and allocate that disk to the NFS server in this image, which is a custom created image that I have right there, which is my NFS server. And I grab a disk, this disk to be specific, and then run NFS server using that disk as the storage. So if you now look at my disk system in Google Cloud, you will find that disk by that name. So I'll go to that disk locations right there. And here you will find a disk called NFS disk. It is a persistent disk, 200 GB capacity total. And it is actually an SSD. So it is an SSD persistent disk, as you can see. It has high throughput, high read and write IO per second, and sustained read and writes are also good. So I deliberately chose a high-end disk as the foundation storage for my NFS server to begin with. That's what I'm looking at in line 34 on the lower left corner, right there. I'm defining my file system type on the disk. So when I ask for the disk, it gets already formatted by ext4 type. And I take that volume mount and connect it to this container in line number 17 right there, which is my NFS server. You can actually read that code is open. You can see that code. How do I create my own NFS server? If you go to GitHub and Cloud Genius, what's the name? NFS server, I think. It should be openly available. No? Where are you? I thought I published it. Maybe not. But I have it here. And here's the Docker file for that. So it's fairly simple. Uses CentOS, installs NFS utility, clean, and create a folder called exports, and then run the NFS server itself. And create a simple sample example index file and expose certain ports for NFS to be able to use, and define the entry point as the run script and the folder to expose as NFS exports. That's pretty much it. So like fairly few lines of code to construct my NFS server. And that is what this server is, grabbing that disk. NFS disk is the name I choose. You can choose any name you like. The name of the disk is important because it has to match the name that you saw here in the disk section. And that is the disk I'm using as the foundation for the NFS server here, exposing certain ports, these ports which are necessary. And then I'm providing this mount path, which is what other containers will use that mount point and mount the actual files in there. That entire disk will become available to all the containers in read-write many fashion. Because this is my network attached storage that I'm using as NFS export, that's what I'm using to create a method of sharing that disk with everybody. I mean, every container inside that cluster. This is, I call the poor man's way of doing NFS. This is functional and cheap. That's why I call it the poor man's implementation. Poor man's NFS server. The proper way to do NFS for a production deployment is not this. I'll show you the proper way also. The recommended way to run NFS is actually expensive. So I don't spend that money. That's the only reason why I use the poor man's method. But if you want to run NFS on Google Cloud, NFS, ZFS, what's the name? I think that should bring up. So yeah, single load filer. That's the right recommended method of running a NFS solution that uses under the hood ZFS file system. That's the Google's recommendation to run NFS in Google's cloud. Although they are claiming that this file server is not an officially supported Google product, you are responsible for maintaining and managing the server. So, but that is on their website. It is a much better approach to running a high-end NFS storage solution compared to the one that I'm looking at right now is the poor man's implementation. Just remember that this example that I'm giving you is a poor man's implementation. It costs me like $10 roughly speaking every month just for the storage pieces. If you go the proper way, it will cost me about like $200 to $300 roughly for a similar size solution. So it is already a lot cheap, and I don't want to waste money. And this method is good enough method. It's not highly reliable, highly available. It's not GlusterFS, but I think it's good. It works out okay. I mean, for me, it's absolutely not appropriate for high-end enterprise usage, not at all. So just remember, this idea that I'm talking about is the cheap way of doing things, not the best way. It works. I mean, you see it. It is live in production right here, for me at least, and you use it. And I hope you haven't had a downtime with it. But we will create downtime, don't worry. That downtime we will create because we will actually knock out the machines out under the hood. So this whole thing running is actually the poor man's NFS solution under the hood. And I hope you are clear about this, because don't implement this idea in a corporate situation, in a big company. People will laugh at you if you suggest that. Just saying that. The right way to do is the one I just posted, which is that method. That is a recommended method. So use this method in enterprise. My methods, not that the current method I'm describing right now, is not good for enterprise consumption, but good for learning. That's why we have it here. So you will understand the way I'm doing it. You will really understand what's going on without spending a boatload. And then you can run this and run where was that? The one I gave you link. Where did I open it? Then you can run in your company. When the company spends money, you run this. When you spend money, you want to learn, you go my way. You will learn much faster. I promise that. You will really understand how storage works in the context of cloud if you follow these methods. So back to our discussion. What we are doing is taking a disk, which is a disk, just one disk. That makes it a single point of failure, by the way. That's why corporations and high-end deployments will say that this is a stupid idea. Yes, it is stupid. It is stupid. You don't use single disk. That's a single point of failure. So don't do it like that. But let's understand what's going on. We'll in a subsequent exercise, we will remove that single disk, but instead use Gluster, which is a multi-disk, multi-machine, multi-region, fairly complex, elaborate, proper enterprise-grade solution. We'll use that also. But for understanding, beginning simple is much better. So that's the disk, one disk problem right there. Single disk is a single point of failure. So don't go that route, repeating that one more time. But understand that this is the disk. We'll export that disk in this location through this NFS server. And then this NFS server keeps on running. It is actually a deployment right there, here. You can see this deployment right in the live environment. Let me just hook up to the live environment right now. And how do we go there? Okay, proxy. So I am connecting a proxy to the remote location, and I can see the dashboard for Kubernetes right now. And that's what I will open right now in here. So the dashboard runs on this local machine, but actually it is running on Google's cloud somewhere, wherever I have my hosted setup. So this is where you see that there is a deployment for the NFS server, which is not in this list because NFS is running, I think, in a privileged mode. Do I see NFS in this list? No, I don't. So I have to go switch over to the kube system namespace. Where do I see in the Kubernetes the NFS here? No, I don't see it. Where is it hiding? Okay, where are you? Default space, are you here? Oh, there is a next page here. Okay, there we go. So now I see NFS server there. Now this is the NFS server I was talking about, which actually uses that single disk. And you can see that it is running for a month, maybe something like that, a month since the last time it was started. And that is the current deployment that I have running as my storage server. Now what this storage server does is exports a bunch of different mount points, like mount F1, mount F2, mount F3. Now let me go show you the actual mount points available in the actual deployment. So I'll open up a connection straight to the NFS server itself. I'm going there right now, making it a little bigger. And I will now connect to the NFS server. So I connected. And here you will find that these are the mount points that I have defined. One of them is this folder that is exported as an NFS export from this container, which is the NFS disk container, which is the one that I mentioned to you about, is the one that exports a variety of mount points like the Cloud Genius website, the hold area, some restores, some streaming solutions. And this TCS is the example I was talking about, is a WordPress solution. There is a traffic folder, there is a videos folder. There are a bunch of other folders. So these folders are exported internally within the cluster to other containers so they can mount these folders. It is in read-write mode. Multiple containers can concurrently read and write because that's what NFS is, giving you the ability to do that. Now let us come out of this container right now. Or rather, before I come out of this container, I want to show you the storage-related aspects for understanding. In our folder called TCS, you will find it contains our classic WordPress deployment. Remember this file just by name, and also this file called active plugins list. And I am currently looking at our MNT folder, MNT, which is containing these details. And I can say PWD, or rather go to TCS again, and then list the whole thing. and say PWD, and just notice that we are looking at MNT TCS, and we are directly in the NFS server itself. So just remember this path and this file as a reference, and I will now exit. I will now go to the TCS container, the other container I'm talking about, which is the one on the left top, that container, which is running WordPress. It is called TCS. And so I'll go to that container now and find out the file system mappings between that container and the NFS mount. You will notice something unique and something very familiar is that file and the active plugins list. And the path definition is var www html, which is mounted as that path mnt / tcs in the NFS server, right? If you remember, this path in the TCS pod is mounted from this path in the NFS server. Now let's go compare that with our notes in here. You will see that the path mapping is the mount path used, and the volume used is the claim name TCS. This TCS claim comes from this claim right here. And the name is TCS, and it is in read write many mode. It exports the storage available 20 gigs, which is claimed from this 20 gig as the volume, and it is claimed from the TCS path from the NFS server pod. So that's the end-to-end look at actual file exported from one container, mounted to another container, and mounted to a different container in a different point, which is where I want it to be. I want to store my var www HTML data in a safe location away from the container in a NFS location, mounted through the NFS server container and persistently stored in a persistent disk. So that's the whole loop of maintaining your storage and keeping it separate from the actual containers, as you saw in this example. So up until now, we have discussed a couple of concepts. One of them was this idea that I just described to you, volume claim and volumes. So you begin with a volume definition, which actually needs some physical storage somewhere of some sorts, whether it is cloud-based storage or disk-based in your company. Some storage has to be there, like NFS, iSCSI, some type. Then you create a volume, and then you have to have a volume claim corresponding to it. And this claim has to be put on a given volume. Like in our example, we had MNT / TCS as the volume, and we claimed this specific claim onto that location, and we internally then mount it in var www HTML as one example. So what you're looking at is a concept of mapping volumes to volume claims and keeping the actual disk completely separate in a third location, like outside somewhere. And by doing that, there is a great benefit that you will see in live, which is, you can erase your container and bring it up, and Kubernetes will help you remember the volume claim relationship, and will always automatically map the exact same path to the same container that comes up online. So you can go and shoot a container, no problem. It'll resurrect itself because it's a deployment. You just don't run a container, you actually create a deployment, and it will maintain that deployment and make sure that it keeps on running for you. And whenever it happens to die for some reason, it will come back online with life again and associate itself with the correct set of volume claims. So you always are guaranteed to connect to the same set of storage resources that you expect to be available. And that's what we are looking at as an example. So we discussed a bunch of other things right now. One of them was to begin with, understand nodes and node pools. We talked about deployment. We talked about volume and volume claim. Now, a couple more things before we get into an exercise. That idea of a deployment, with that comes another idea, is to run a service. And let's go see what a service actually does. And so service basically is something that exposes a deployment. Let's think of it that way. So service exposes a deployment. Let's see what it means with an example. So you saw this TCS deployment. You saw the corresponding TCS persistent volume and persistent claim. You also saw the actual NFS server, which I'm going to close this window for right now. And I will bring up the service corresponding to the TCS deployment as an example. So I'll go find that service. And bring it up on the down window right there. So service definition is very, very simple. You can actually find it amusingly simple. As I said, a service, what it does is it exposes a deployment. That's all it does, right? So let's go see that in real example. I think it is appropriate to close this window for right now and put these two side by side. So let me do that quickly so we get a clear idea. So on one end, I'm going to open a deployment, which is the TCS deployment once again. And on the other end, I will open a service corresponding to the same deployment on the right side. And now you will see what I'm talking about when I said a service exposes a deployment. This service on the right side called TCS exposes a service selected by the selector called role:TCS at port number 80. That's it. It exposes the TCS service on port 80. That's what it means. That's what service does in this example. So what you're looking at in simple terms is the portion on the right side here exposes the portion on the left side on port number 80. There is no port reference on the left side, but there is one on the right side at line number 8. So when you do it this way, you're basically exposing the WordPress instance, or rather that container deployment, on port number 80 as a service. And now what you can do is use that service exposure to construct an endpoint or hook it up to some kind of an endpoint. What does that mean? It means practically something like this. So you have a deployment that runs a bunch of containers. In our example, the TCS deployment, we have a service called TCS, which exposes port number 80 and actually maps to this deployment. And then I want to make use of this, and I want our users to be able to access this, right? So I would like to have a way to let our external outside users visit and access this service, for which we have to let them in. Let them in. And this let them in is a concept known as ingress. So now you have to define an ingress. An ingress is a way for people to come in, to visit your service. And you will see that, the simple things that we have been discussing all along are unnecessarily seemingly complicated. Like, you have layers and layers of what I call indirection or abstraction put in place to hide simple things like a complete deployment hidden behind a service and a service hidden behind an ingress. And what is an ingress? So let's go take a quick look. But practically speaking, it will be something like this: http://somewebsite.com. Actually, it will be the tcs.com. That's how I have named it. So this tcs.com goes straight to this 80 service exposure at port number 80. And that here is an ingress definition. We can actually visit it right now. We can go to this site and see what it shows. So let's go there. But before I go, let me see if I can look at the ingress definition also. So let me see if I have an ingress defined here for TCS. And I'm going to split it on the right side, or maybe the left. Hold on, let me go bring it there. So I'm splitting the ingress definition on the down portion, right down. And so that is my ingress definition right here. You can see and already understand this ingress by just looks of it. You can see that it defines an ingress that has some annotations, but let's leave the annotations aside for now. Look at the specification. In there, we have a rule that says if somebody visits this host name, thecloudseminar.com, which is, by the way, TCS, the cloud seminar, then you ask for the slash path, meaning the root of the URI or the uniform resource identifier. Then you connect them to the backend service called TCS at port number 80. That's it. That's the definition right there. The simplest form of a ingress is in line number 10 through 17. What we are really saying is if somebody visits thecloudseminar.com, you let them in and send them to the TCS service, which is right upper right corner, TCS service defined right here. Spec port number 80. And it selects the deployment defined in line 10 by a selector in line 10, which goes straight there, matching the label at the selector level and looks at this deployment and shows them this container. That's how the whole traffic flows from the outside. So if people visiting the cloudseminar.com, like I will do now, I will go to the cloud seminar and open it up. I'm a visitor from the outside and I reach that endpoint of the Kubernetes cluster. It looks at this service definition of the ingress and it identifies the host, the visitor with this name wanting to access some resource. So where do you route that user? The user is asking for a slash path, meaning the main website itself. You just route them to this service called TCS at port number 80, which is running here. And so you know that that service can select using the selector called role:TCS as the selector. So look at the matching label right there, and you have a deployment running. And therefore, whenever a visitor visits this site, it actually hits the service. And then that service gets directed toward the deployment, which shows you the container, which is what I'm running here. And it has a matching volume mount claim at that location, which stores the WordPress content, which was visible to me when I visit here, and all that good stuff. So this is how you construct an end-to-end flow of components, which is what I'm building towards. So what I'm really trying to give you at this moment is the conceptual understanding of various components that build together towards a Kubernetes cluster. And there are a small number of details that are also important, but not critical for us to actually begin our exercise. So therefore, we can take a look at what those details are, and there are actually quite a bit of them, by the way. There is a cron job that you can see here, and I can maybe quickly walk you through all these other elements that I did not describe too much in greater detail. I described to you briefly the idea of a deployment, which is where you'll see a list of deployments coming up on that website, which is a local host location, by the way. And this local host is mapping through a proxy to the Kubernetes cluster I have, which is a proxy connection I have established right here. And you can see I'm running a proxy on my local host port 8001 right there. And that proxy is what you're looking at here. So it looks like localhost running 8001 on that port, but it is actually the Kubernetes cluster showing me the deployment dashboard where I'm looking at my deployments, and I have a bunch of them. The one we looked at today was the TCS deployment right there. And I have a bunch of other deployments right going alongside. So collection of services running, collection of deployments running. But the one thing that we discussed is that this website, the Cloud Seminar website, this one, connects to an ingress. So there are ingresses defined. There are a bunch of them also here. They all go to the same IP address, by the way. This is the same endpoint for every service. They just expose one endpoint. This is the static IP allocated to my cluster. So I just send everybody to that endpoint. You can actually check that out. You can see something like let me come out of it and say dig and find its IP address. And this is the IP address I got, and this is the IP address that I have for static IP for my cluster. And this is what you will hit through the ingress. So you know the idea behind ingresses is that this TCS that you look at is one of the ingresses that I have in my list of ingresses, which connects to this service. So I have a bunch of services also running. The service of my interest right now is the TCS service, which is what is running here, and it connects to a pod created by the deployment called TCS. The pod name is also TCS. Using the same name for a pod, for a deployment, for a service, for the ingress, to make it simple for me to understand how the traffic flows all the way through the cluster, all the way to the end where I have the application itself running. So here you see that the actual pod, its CPU usage, its memory usage, and a bunch of other characteristics and other parameters that you're looking at. There are a couple other examples here. For example, this idea of a cron job. So here I run a backup system that automatically backs up the entire setup that I have here every morning at, I think, 8 o'clock or something like that. I don't know what that cron schedule looks like from a cron tab perspective, but essentially what it does is it goes to console. It goes to Google, sorry, what cloud is it? Amazon cloud, and backs up in a bucket. So it takes my Google container cluster and backs up in the Amazon S3 bucket. That's how I wrote the logic of backup, is I back up my Google container cluster into Amazon's bucket system. So you can see that bucket backup happening in S3 in a bucket I have, I think I call it logbacks. And there it is a weekly backup going on right there. In fact, the last backup you have is a February 25 backup that happened 7 o'clock yesterday. So it is a daily backup. Every day it runs, and it's a rolling 7-day period. So that's what you see, and that is showing up in form of tarballs preserved in a bucket that is created through a backup cron job that runs right here in the Kubernetes cluster. And we can go into details about how you configure these things, but that's the backup job, runs every day. There are other things like daemon sets, which I'm not using. There are deployments, which I'm using quite a bit. You can see some of them here. There are jobs that I have, and these jobs are the actual backup action jobs, and one job is running right now. This job is the cron job that runs WP cron to ensure that the site functions correctly the way I want. There are a couple of things that you need to run maintenance-wise on applications on a every so often basis. So you can see that something is currently running right now, and so that is starting up. You can even go and inspect it, and it is running. As you can show, some job is running, so you can go and see and inspect and see the logs right there. And you will see what it does. So it will show you what it is doing right now. That job is doing something on the back end of the website. I don't know which website. There are probably a bunch of them. There are 4 or 5 websites run here in those 2 machine cluster that you are looking at. So it is doing something right now. We'll talk more about what it does. But essentially, it is a repetitive job that I need to run every so often. So I do that. And I run them as jobs, which are listed right there. And so there are some WP jobs here, and there are some backup jobs. Backup jobs runs every day, like 24 hours. Then there are pods. These pods are constructed based on deployments that I create. So I create a deployment. The deployment generates these pods. Some of them are actually jobs that create a pod. For example, the backup actions. This one, these 3 actions. Sorry, I clicked the wrong button. Go back. So backup as a job also can kick off a pod. A deployment can also kick off a pod, depending on longevity.
Can you define what a pod is?
Yeah, pod I think I already defined, but I'll repeat that. Is a collection of containers.
Oh, okay. So it's just a collection of containers,
Correct.
but you're not defining it in your YAML file. It's defined. It's automatic, is what it sounds like, right?
Yes. A pod gets
Okay.
created as a consequence of you setting up a deployment. So
Okay.
this
Thanks.
will become a pod. Similarly, you have a job defined. For example, here is a pre-compiled job that I don't use currently. And that is also a collection of containers, which is basically a pod. But then you define it like a job. And job is like a one-time operation, whereas a deployment is a perpetual operation. So it keeps on running. The job can be a one-time thing. Oh, do this one time for me, please. So it'll go and do it. Like a pre-compile operation. So I want to compile something before I run it one time. So here we go. Run the job, one-time operation. It starts a new pod which contains multiple containers. It does the thing and then it is done doing things. So then you're done. That's how it rolls from a job perspective. But you don't actually define a pod as such. You define a deployment or a job or things of that. That a pod basically is a collection of containers. So a p pod containing many p's, or whatever the round things that you have inside the p pod. They're called p's, right? Yeah. So where was I? Here. Replica set is something that also gets created when you deploy a deployment. And this is the one that makes sure that the deployment runs. So you can come and arbitrarily shoot down a pod, which I will do right now. For example, just for the kicks, is I will say, look at my TCS running pod and just kill it for no reason. I'm not killing it right now. I'll rather kill a more critical one to demonstrate. So here we have a pod, and the more critical one is the cloud. Where is the Cloud Genius one? Next page. So here, the Cloud Genius pod that is currently running our website, the actual main production website, this one, I will kill the pod right now. You'll see it. It'll be fun. It'll be fun. It'll cause some blip, and that's okay. So let's go shoot it down. So here is my pod. It is the actual production pod running for, I don't know how many, how long. It is running. And what I plan to do is just go crazy like that and delete it. And you know what happens? A new container starts without me doing anything. Already started. And the site should not be even impacted, I suspect. But let's go see. So we are going to refresh the screen to see the pods we have, and our Cloud Genius pod should already be functional by now. And where is it? Okay, where did you go? Hello. There it is. It came back up and running. The pod is already functional. 29 seconds ago it started, and the site should be completely functional as is. So that was like very, very minimalistic in terms of destruction. I did not go havoc, did not throw a chaos monkey at it yet. But I will throw chaos monkey also. So you saw I killed a pod, no problem. It doesn't even bother users. Users don't even notice from outside that the pod died. Unless there is a critical long-term failure, in which case people will notice. So you can kill pods, no problem, left and right, and these replica sets actually make sure that the pods are alive. So this is the control logic which kicked on a new pod running the Cloud Genius website. In that location, you can see that it came back up and running a minute ago. And is running right there. So that's the idea behind a pod and a replica set. There are a couple more here, like replication controllers, which I'm not using currently. Stateful sets I'm not using currently, but they are there, available. We'll discuss them. We have some ingress routes. These routes define how applications can come in. For example, here is the TCS ingress. You can edit the YAML underneath if you want in the dashboard. Here is the entire YAML for the ingress. which you already saw, by the way, in my notepad. You already saw the ingress. It is right here. And that is this ingress defined for the Cloud Seminar website, which you maps to a service, which maps to a deployment, and that's how it rolls. Next, we have some services defined, which are corresponding to every deployment that I care about to expose it. Sometimes there is no need to expose a particular deployment. You just have it running internally to do some back-end job. In that case, you don't need to have an exposed service. You can just leave a deployment, only just a deployment running, and that's okay. You don't need to. But here are certain cases in which I want to expose them to the world outside, so I do it. And so here is the exposure of TCS as the ingress, which maps to the pod corresponding, and bottom line that you saw in our TCS ingress, which I think I already showed you. Did I? Yes. Okay. So that is ingress, where you define incoming routes. There are a couple more things here, like config maps, which is the idea here is to store details about configuration. And then there are persistent volume claims. These are the claims used by a variety of containers, a variety of pods against my NFS server internally. And so these are the claims that I have. They all have a different name, unique and distinct from each other, and they map to exported areas from the NFS server, which also happens to be run as a deployment. And you will see that that particular NFS server is not externally exposed, but it is internally available as a service. You can probably see that somewhere here. NFS is available as a server, but it is not exposed externally. Externally, there are no endpoints available to NFS. It's only internally available at these ports that are necessary for NFS to run. So I open them only internally, and that is the IP address of my NFS server internal to the cluster. Externally, nothing is accessible. Then we have some secrets, and these secrets are actually secrets. So I should not be showing it to anybody. So I'll not show it to you, by the way. Maybe I'll show you something which, what can I show you? So secret is basically secret information, like you saw a data bag in Chef server, right? You store them encrypted. So let me show you this secret. So here is the basic authentication secret. Click. And you can see that the name of this secret is basic authentication. It is opaque, meaning even if you click on it, you don't see it. But if you really, really want to see it, you have to hit the I, and it will show you the secret content, which is like that. So that's the secret. I'm storing a username and password for just kicks. I don't actually use it. That's why I felt it okay to just share it with you as to how you store secrets, and they are hidden from view unless you want to see it. And you can disable this capability to expose itself. You can also set those parameters and hide the secrets from becoming visible if you like. But secrets are also YAML files. So you can go back here and look at my secrets right there. They are also YAML files, and you can actually match that secret right there. So this is the same secret that you saw somewhere in the website, which exposes the, is it the same or different? I think it is the same. This is the opaque secret which exposes the value. Where is the value? Oh, this YAML can be complicated. Where is the, oh, there is this authentication. This is the auth data, which is a base 64 encoded representation of the secret that you visually saw. So this actually contains the secret, but it's encoded. So you don't read the same way like you saw in the browser, but it's the same secret. Auth.yaml is the representation of the secret that you have to create. And you can use that secret in any place that you want to use, but I'm not using that particular secret. There are a bunch of other secrets I have in the secrets folder that I will not be able to show it to you because most of them are actually SSL certificates and they're live in production, so I'll not be exposing them to you. Now, the other things here that you notice is this idea of a namespace. And I was looking at the default namespace all along. But then there are two more. And you can create custom namespaces if you like, just by clicking the create button and uploading a YAML through the browser interface, which is not how most people do, by the way. They will just deploy it through some K command, kubectl command, like I was playing around with here. In this proxy is running a kubectl command, the K command. I have shorted it, made an alias for that, which is what you're looking at. This namespaces are basically a way to classify your deployments, your services, your pods in your containers and other things in terms of smaller subsets. So here in my example, I have only 3. You can create more if you like. The default one is how the default is given. This is the one that you get by default. And I did not go have a customizing in further because my setup is not that big. It's a very small one. We have some nodes defined here. And I know I only have 2 nodes, and these are the machines available, 1 and 2. 2 machines, total memory used is about 10.2 GB, and total CPU usage is fairly low. That's the current state. I have some persistent volumes defined. These are corresponding to the same thing that you saw here is the volume claim, one-to-one relationship between a claim and a volume. A volume is basically an NFS export in my example. You can make it use anything you like, depending on whatever cloud service or data center service you have in your company or in the cloud. Here are the volumes that I'm currently using. You can also specify some roles, which I'm not saying, these are default roles available. I'm not specifically creating any new role as such. And you can also further expand and create your own storage classes. Like you can have high-end storage, or you can have a low-end cheapo storage, and basically the classification of storage levels. You can create classifications and appropriately create persistent volumes that cater to different classes of storage, like expensive, fast storage, cheapo, slow, fat storage, things of that nature. You can define classes and appropriately allocate slow storage versus fast storage according to the class name selection that you have, and then go and create a persistent volume to cater to the type of class that you have. So I have only one class, which is the only class, which is the only disk I have actually. You heard me say it's a poor man's implementation, as I call it, and it is not the best enterprise grade implementation that you can think of, because I don't want to waste too much money. It works for me, so that's my solution. It is just for me. Don't take it to any company, please. Having said, now is the time for us to actually put these things together in form of this exercise. This, by the way, is an exercise. It's a fairly elaborate exercise.
Can we do it after the break?
Yes, after the break. And I would like to make sure that I complete it today. So I will run it. Let me break that proxy. And I will like to run it in a situation where you can also do it yourself. So you may want to do it with me, or maybe later on, it's your choice. But what I want to do is make sure that I run it not on the Macintosh. That's what I'm reminding myself. Please don't run it on the Macintosh, because other people will not be able to. Some people. So that's why I have the Cloud Genius workstation going. And I will be using that. And so that is my plan. So I will, we have Raj. Hey, Raj, can you hear me? Raj?
Yes, Nilesh.
Hey, how are you doing?
I'm good. I'm good.
Good to see you. We are doing some taking a short break, and then we'll continue our exercise on Kubernetes. When did you join? When did you join in?
It's like half an hour before.
Half an hour. Okay. Okay, good. Are you able to hear me properly, see me, and everything? The audio,
Yes.
video is good.
Yes, yes. Audio is like I can able to hear properly, as well as I can able to see you also properly.
Okay, good to know. Good to know. So I'm just starting a short timer, break timer, and we will continue after the break. Right now, it is this is the time left for the break.
Okay, thank you.
Yep.
Nilesh, that exercise you're going to do is that one you're just showing, Kubernetes the hard way?
Hard way. Yes, correct.
Can you post the URL, the GitHub
I will do that.
URL,
Yes, yes, yes.
so we can clone?
Yeah, yeah. I'll grab that URL. It is, most of it is simple to accomplish. It's just a fairly long exercise, and the hardest part is to understand what it is. That's what I will elaborate on. So as we go along, doing it is not that complex, by the way. But the more important action from this exercise is to understand what does it take to run your own Kubernetes cluster in your company. That's the focus, right? So if you want to run it for real, for yourself, on your own boxes, this is the way.
I wonder if there is a cleanup needs to be done on our machines to remove maybe something that runs on HTTP or something like that.
Can you please tell me what would that be?
I don't know, Nginx or something. From
Yeah, it will not interfere. So don't worry.
Okay.
Not interfere. So there is nothing locally deployed on this setup. So everything is remote. So you will use Google Cloud in this exercise. You will have to have a account with them, which I think you have already.
I might, but they. Let me see.
This is a Google Cloud exercise. So it will expect an account with your Gmail login. So that's the expectation.
Huh. I forgot my password. Okay. Google Cloud Platform. Open URL. Oh yeah, okay. I have $300 remaining.
Yeah. Google gives you $300, so that's good enough money for running this cluster for a full month. So no problem.
Okay, cool.
Yeah, but don't waste all your money in just this one exercise. Yeah, leave some money for your other exercises or for other interests that you might have.
I am setting up OpenStack.
Okay.
I will never run out of money.
You're big people. You're not like you don't use the poor man's NFS server. You probably don't have to.
No, I'd say it's currently it's 32 gigabytes dual Xeon.
Wow.
Yeah, I'll probably expand it to 64 gigs just in case.
Yeah. When I run, you saw my setup. I showed you the whole thing. I spend only $300 or roughly something like that a month. Don't want to waste too much money because when I don't have to, why waste money? That's how I think.
I'm also looking at installing the Pi-hole on my DDWRT router.
Wow, you will be the fourth one to do that, by the way.
Okay.
People apparently like it so much. The moment people talk about advertisements getting cut, and people jump on it. The moment I talk about it, people jump on it.
I'm contemplating doing a standalone box and just pointing individual computers, or doing the whole house. Because I don't know what I want to do yet. Probably individual machines are better.
Yeah, individual. That's how I run it on this Linux box here. Just run it dedicated. But yeah,
I was thinking I would run actually look at getting a Raspberry Pi, because I've been wanting to play with those anyway.
You too, Rob? You'll be the fifth one.
Yeah. Well, there's a couple other things I wanted to look at the Raspberry Pis for also. So, and since they're super cheap,
yes,
it's easy to get. So
yes. In fact, the really cheapest way is to start a new virtual machine in your VirtualBox and bridge it directly to your home router, and then test it thoroughly first. And then you spend $10, $15 on the Raspberry Pi if you want. But even before you go to the Raspberry Pi direction, just use a VM in your virtual machine directly here.
I'll be doing that first just to learn it. And then the other thing that I was thinking about is I need to do research on a new router, because I want to get a new wireless router that does pretty much, it's going to be for quote gaming, but I have so many people coming in and going and so many devices here. I need a wireless router that also I have wired computers that I want to be able to do.
So use this solution.
What is it?
You look at my screen.
I am, but I'm not seeing hardware. I need
Correct.
actual hardware.
Correct. Yeah. So what you do is you make sure that your hardware of choice is supported on this software.
Oh, okay.
So this is an open source router software.
Yeah, but the problem is finding a piece of hardware that will have enough RAM so that you can have, a lot of the problems with routers is they only have enough RAM for maybe 10 or 15 MAC addresses, right?
So here are the list of routers that are saying that they are supported. So you look at the list.
Okay.
And so it's a database of router supported. So just go to that database.
So what is that called?
DDWRT.
DDWRT. Okay.
You look at the router database and you put in the router company name right there. You have in mind, say Linksys is a good one. Just type in link and you'll get a long list of things. And then you select your preferred green colored supported list.
Yeah. I'll have to play with it.
Yeah.
Because Linksys and D-Links I stay away from because they don't have.
They just use whatever you like. I mean, so say I use Buffalo. Buffalo is my preferred. So you say type Buffalo and then you enter and you get a long list of Buffalo routers. That's my preferred machine set.
Huh. Okay. But what I don't see in there is a amount of RAM. Because that's the big problem right there is the power output. So I want high power output.
Here's your RAM definition. Is that
there
good
you
enough
go?
for you?
RAM 64 megabytes. Yeah, that's really low. I want somewhere in the 256 to 512.
So just search for it.
Megabytes.
So just make sure that DDWRT is supported, and then you buy the biggest possible, biggest, baddest, meanest router you can afford.
Yeah.
Why not? I think we timed out.
Thank you.
So
Yep, thank you for that.
Let's go switch. Okay, so let's go. And first thing first, you will need to use a Google account, a Google Gmail account with access to $300 freebie that you probably already have. And create a new project here. So in my organization, I already have created a project called Labs that contains nothing. And I'll be using that project right here in our exercise. So that's the requirement ingredient. We'll also use the virtual workstation we have already at hand. That is what I will be using, so that this workstation will be useful as is. And we are not running anything directly on this workstation itself as such, not too much. And so there is no collision conflict or Nginx coming in the way or any such thing. There is no issue there.
How to create an empty project?
We will go to this site and say click, and here you say plus, and you create an empty project.
With a specific name, right?
You can choose the name you like.
Okay.
That's one way. There is another way on the command line. We'll go through both methods. So we'll begin. This is the hard way. It's more of a name to scare people away or to maybe attract people towards it, depending on the level of comfort. It is not actually hard. Let's see it. It's not hard. It's just called the hard way because the other way is really, really simple. So this is the hard one. The prerequisites are, let's go figure out what the prereqs are. You need Google Cloud Platform. You will spend about 22 cents per hour, which is amply covered already in the $300 free credit you already have. So it should be okay. Having said, we need to set up this thing called gCloud. gCloud is not set up already in the VM. So we'll go to the documentation section right there on that link, Google Cloud SDK, and we'll set it up like that. And for it to go, we have to go on the Linux setup, not the Windows or Mac. And we first thing check whether we have Python or not, which we do. So we'll say Python. And for simplicity, what I would like to do is this copy and paste between Mac and Linux is kind of a nightmare. So what I'm really trying to accomplish is to simplify my keyboarding a little bit. And what I'm doing is still using the Linux command line, but through the Macintosh command line. So my copy pasting will be a whole lot easier. What I will do now is SSH to my virtual machine like that and type in the password Cloud Genius. And I'm connected to the VM right now, right there. And this is the Linux machine. So what I would like to do now is move this window down a little bit and hide it like there. and use this command terminal, which is basically the same command line. As you can see, it is Linux. I'm just connecting it through the more friendly Macintosh terminal. It is more friendly for my keyboarding because there are lots of keyboard steps involved. So I would rather not go, and run myself into a havoc. And I want to finish this exercise hopefully today. So let's go do that. That's the reason why I am using my Macintosh terminal to remote connect to the virtual machine right on the same Macintosh, and then running these commands like Python -v. Check my Python is good. Next one. We have to now install Google Cloud SDK using this one simple step, which I think I already have. So I should be able to test. You can do that step, but I'll say gcloud and find out whether I have it already installed, and it's not found, which means I need to go and do that. So I'll install it. I'll say here, I need to grab these. Oh, by the way, hold on. Before I jump too further, there is a specific custom-made package for Ubuntu. So you should use that, not the generic Linux package, but use the Debian Ubuntu package. It's a whole lot easier to go that route. So please don't click on the Linux button. Click on the Debian Ubuntu button. It's an easier option. Use this one instead. You can go the Linux route also, that will work, but this is a whole lot easier. It is customized for Ubuntu and our machine is Ubuntu, so why not use that one, Ubuntu? And therefore, we are getting a environment exported, which is basically grabbing the release version that we have and exporting that like this. It's a quick copy and paste. All it does is LSB release, which is our release called out. That release that we have is Trusty. So that release name is showing up like this, Trusty, and that gets exported in the Cloud SDK repo variable in the environment. Then we add the Cloud SDK distribution. So that line will grab a distribution and map and create an entry in the apt sources. So like that, you will ask for a password. The password is Cloud Genius, and we add that entry in our apt list. You can see that entry showing up here. In sources list, you have a folder called Google Cloud available now. Let's go. There it is. So that list, that entry got created as a consequence of this last command. What I will now do is add the key pair corresponding to the Google Cloud Platform's public key. So that key is available from that location. We'll include that. And then we are able to update our apt cache and install the Google Cloud SDK through a sudo apt command like that. So it will install it. Much easier than the other option, which is, the other option was the Linux option, which is slightly trickier. This is a whole lot easier for Ubuntu and Debian. That's why we are choosing that method. It says, do you want to use some addition? It's asking a yes or no question. So we'll say yes, go ahead, do it. And then we'll initialize the SDK. This step is a Docker step. We are not doing this step at all. We'll proceed further with initializing the SDK package. The initialization involves us in logging on to the command line on that Linux box that we have running on our laptops and hooking it up with our own Google account. Once the SDK is set up properly in there, we will then hook up and initialize our account, and it will ask us to log into Google like this. I'll say Google Cloud Init, and it will say, okay, I'm going to check my connection. You must log in to continue because I have not logged in yet. So I'll say, yes, please log in. And it says, okay, open that link in the browser. So we'll copy that link. By the way, this is going to be slightly different for you if you're running directly in the VM, not like me. It'll actually open the browser right there for you. Whereas in my case, it did not open the browser. So I will open the browser manually, hit that link. And here it will say, please log into Google. So I am already logged in. So I will say, select my account I want. So I'll select this account right there. And I'll say allow. And that gives me this token. So I'll grab that token and provide it to the Google Cloud verification code right there, and I'm logged in. Now, once I'm logged in on the command line, it is asking me to select a project to use right there. Now here you can create a new project if you like, but I have already created a project called Cloud Genius Labs. So I'll select that project already. Number 1, the project has been set to Cloud Genius Labs. Do you want to configure a default compute region and zone? I say yes, yes please. Because what I want to do is stay closer to my customers. So I'll select my zone as, I'll say yes to it first. So I'll say yes and say, okay, pick your region of choice. So here I think my choice will be US West 1. Let's go see what these guys, actually they have given us a choice for us to use in the exercise. It makes it easy on us. So we'll just use their choice. I think they gave us a choice somewhere here. So not in this Google Cloud SDK setup, but go back a step to the exercise, the hard way exercise. That's where you will find that it actually suggests that a particular compute region, US West 1C, be selected. It is not a requirement. You can still go choose any region you like. This just makes it easy in copying and pasting. That's the only difference. So I would like to match their region choice, US West 1. Now US West 1 C in specific. That's the copy paste ease of use idea. So I'm going to match this US West 1C, which is number 12 in this list. So I'll just match it, okay, number 12, US West 1C, because I am lazy. I want to copy and paste from the left side into the right side. That's why I'm choosing number 12. That's the only reason, by the way. There's no other reason. And it prompted us to do something. It has selected us the Cloud Genius Labs by default, US West 1, US West 1C by default. So all of these things are already set up. Let's go see now. We have to do something like installing the client tools. So there are some client binaries need to be installed on this machine, on the Cloud Genius workstation, that are not there already. Those 2 pieces of software are from Cloud. What's the name of the company here? I think it is called Cloud, what's the DNS company? Might be Cloudflare. So Cloudflare provides a package of SSL tools that are necessary in this exercise. They give us a easy way to generate SSL certificates, establish a PKI authority and all that. That is what we are using, the Cloudflare SSL library. It is available for OS X and Linux. So I'll focus on the Linux aspect. And we need to, first of all, grab those binaries. The binaries are currently not available in our folder. So we'll grab them. And it does not copy and paste properly because the command show progress is not valid for this particular implementation of operating system. So we have to remove the show progress portion. This thing is not supported in Trusty. What does that do? We'll go back a step, remove the show progress thing, and then it will download just fine. That show progress feature is not available in this version of Linux. So we have to remove the show progress like that. And then hit it. It will completely successfully download the whole thing. They are now available here. 1 and 2. Those 2 binaries are now available locally. This show progress piece hurts us because we are using a version of Trusty Linux that they never tested with. So they have this show progress flag in there which need to be removed, which I just removed. So now I have those 2 binaries available. Those are not executable quite yet. So I want to make them executable. So I'll do that. chmod, make them executable, please. So I did that. Now they are executable. You can see RWX showing up. And then I want to move them in a binary location where I want to keep my binaries. So I move them away and now they are not here visible. Actually, one of them is gone. The other one also needs to be moved to the binary location, user local bin. So I move that one also. That also is gone. Now let us go check whether we have any files locally available. Sorry, whether we have any of these binaries locally available. No, they are not. Now can we check our CFSSL version? and apparently so. So it is matching what they show here. The output matches item by item, which is expected. Next, we have to install a binary to connect with our cluster. This binary is called kubectl or kubectl or kubectl or whatever you want to pronounce it. That is available for OS X and Linux. We will focus on Linux and we'll grab that binary. And it comes. So when it comes, we'll chmod it. And then chmod it and then look at that binary right there. It is sitting right there. And I want to move it to user local bin. So I move it. Then I verify the client version of Kubernetes to see whether I have the correct version. Looks like I do. Then I will provision some compute resources in the Google Cloud. I'll go to the next step in the page, and here I want to configure some compute resources. The first thing I want to do is to define a private network. A virtual private network, virtual private cloud network is basically a VPC in their language. So in Amazon language, they call it VPC. What we are doing here is creating a bunch of networks. So we'll first of all list out all the networks we have currently. So G Cloud Compute Networks list. And so currently I have nothing expected. It's a new region, by the way. So I will now create a cluster, or rather a virtual private cloud network, and call it Kubernetes the hard way. So it created. Maybe it takes like 2 minutes to create. So it takes time. We'll see it complete. And then we will use that network as our place to create our infrastructure and use that infrastructure to create our Kubernetes cluster the so-called hard way. It's not that hard. So we're waiting for this operation to finish. When this finishes, we should have our cluster network list showing up. It will show us that we have a default regional cluster, or rather default regional network, and the Kubernetes the hard way custom creation that we created as a network. Those are available now. Now in there, what I'm doing is a subnet inside that network. We have to create a subnet, and that subnet we will call a subnet by the name Kubernetes in this IP range. So you can see the IP range here. This range of addresses is the one I will be using as my internal pod-to-pod, container-to-container overlay network. That's the network that I'm actually creating right now, because I intend to use this range of addresses as my overlay in my cluster. And you can see that there is a specific number that I have chosen. So I need to remember that number. This is, by the way, a Flannel network, Flannel overlay network. Flannel overlay is a open source product available from this company called CoreOS. They're acquired by Red Hat now, and they are going to provide us a network called the overlay network for use in our Kubernetes clusters. That's what we are going to do right now. So that is this Flannel thing that we'll be getting onto it pretty soon. Let me close out some of the unnecessary windows and back to here. So creating a network subnet by the name Kubernetes in our VPC in that IP address range. So we'll go and create that subnet. It's fairly quick action. And then we'll proceed with setting up some rules for firewall. Nothing in this exercise is scripted. It's entirely copy and paste. So there is no automation involved, because we really want to understand what's going on. So what we are doing right now is creating a subnet like that, which you can visually see on the Google Cloud. On the visual aspect here, you can see that the cloud shows up a network constructed as our network services. Where is that? No, it should not be in, it should be in the VPC network. We have a network called default and another network called, so this is the default network. which is not what I'm interested in, but I'm interested in the other network called the hardware network. And in that network, we now have a Kubernetes subnet. This subnet has the IP address range of the one I choose on the terminal, and that is constructed correctly. So that's the subset of the subset of the VPC, which is a subnet that we have now created. And this is the gateway, and this is the IP address range available to us. It is private, Google access disabled. Fine. Let's continue forward. Then we have a bunch of firewall rules that we need to create. These rules basically allow certain traffic to flow within the cluster. So pretty similar to what you remember from an Amazon exercise. Here is a firewall rule. A firewall rule is basically security groups in Amazon language. They define what is allowed, what is not allowed. So if you look at this picture, or rather this command line, you will see that we are creating a firewall rule, basically a security group, if you will, by this name, the hardware allow internal access. Let's go see that name one more time, a little bit easier. So what we are doing is looking at creating a firewall rule by this name, allow internal, and we are saying allow all TCP, UDP, ICMP traffic, all within the VPC on these source ranges, as long as it is in the overlay network, and another range of IP addresses, as long as you are in the game, you're in the zone within the network, you're coming from these sources, all traffic is allowed. So we'll say open everything within the VPC. So it is creating that firewall rule, which will allow us to have one machine talk to the other, one pod talk to the other, one container talk to the other, or things of that nature. That's this rule we are putting in place. Next, what we are going to do is to allow another rule that will allow external connections from outside, like me going into my cloud, you going into your cloud, you going to your cluster. That should be allowed. We should be able to SSH. That's why you need to have port number TCP22 and this port 6443 and ICMP traffic, so you can ping your machines if you like. And that's what you're doing, and you're allowing it to open from any location on the internet. So that's what this rule does, is to allow external access. It is not everything like this, but only certain things like these allowed from anywhere on the internet. You allow that, and that is what is going to create another rule. That rule should pop up right here in our firewall rules. As you can see, in the firewall rules section, we now have in our, let's go focus only on the network that we are interested in, the Kubernetes hardware. We have allow external policy and an internal policy. Those two policies are in place, and they allow what we only limit these specific inbound traffic coming from outside are allowed. You can see them created. And now back here, what I want to do now is to list out all the rules. So we'll just say list me all the rules I have in our cloud. And so I will clean up and then print all the rules that I have. And I see that I have two of them, the external rule set and the internal rule set. So those two firewall rules allow these specific TCP, UDP, ICMP traffic all the way internal, any to any, and only certain ports from outside. Next one, what I want to do is get a public IP address. So we want to allocate a static IP to our cluster. So we are saying, give me a static IP. By the way, each of these actions should be possible to do in your data center yourself. Figuratively speaking, the same thing should be possible in your physical data center. If you have such a setup, you can simulate the same thing in exactly by allocating an IP, creating a subnet, and carving out security structure around some firewall rules using some technique that you might have in your company. So the same concept will apply. Not much different, except the actual operations will not be using gcloud commands, but we'll use something else that you might have. Next one, we'll now verify whether the actual IP address was allocated. So let's go see that, whether did it allocate an IP address for us. So we'll see and find out that it probably did. And so it has given us an IP address right there, and it is reserved. Now, a thing to remember in Google Cloud is if you have a reserved IP address, they will start charging you money for it. Unless you use it, you actually allocate it, then that extra bill goes away. That's something to remember. The IP address is allocated and reserved, and now we will create some machines. So what we'll do is create 3 boxes, 3 machines right like this. So it's a for loop. We are creating 0, 1, and 2 machines. So for I in 0, 1, and 2, so basically do this action 3 times. You're creating a machine with a name controller. You're associating a boot disk, IP forwarding allowed. Image you're using is Ubuntu OS. Image project is Ubuntu OS Cloud. N1 standard 1 machine size. You're defining the same private network IP in the same range that you saw and selected before. You're also asking for some scopes, so you can access compute, read, write, storage, read only, service management, service control, logging, write, and monitoring actions. You're putting that in the Kubernetes subnet. You're giving it some tags, and then you say done. You do it 3 times, 0, 1, and 2. So we run it, and it creates 3 boxes. You can see them here popping up in the VPC, in the compute engine side. You will have 3 machines popping up right here, 0, 1, and 2, 3 controllers showing up. And while it does, it will happen in the background. The command is free for us to proceed forward. So we'll now create workers. These are the controller machines. We'll now create some controllers. We'll now create some workers. These were controllers. Controllers are the masters that are available to you. If you go the easy route, they just give it to you. You don't have to create 3 machines like I just did. Because you're using a ready-made service, they're eating the cost. You will spend only money on the workers. So in this example, we are spending money on our controllers as well as our workers, both. Now the worker side, we'll do the similar step, pretty much like that here, and create 3 workers. So like that, 3 workers, 0, 1, 2, and 200 GB disk, Ubuntu OS, N1 standard 1, same pod CIDR address space. This is the pod address space. This is the network IP for the private network. You have some scopes for access to compute resources, storage resources. You put that in the subnet called Kubernetes and give it some tags, and you let it proceed. So you'll have 3 more machines now showing up right here in that section. And you refresh the page, you will see that controller 0, 1, 2 and worker 0, 1, 2 should pop up any moment soon. So it is popping up already. Worker 0, I already see that. Let's proceed forward. We will now verify whether our compute instances are ready or not. So we'll go run that and we'll check it out, see how many machines we have running. So we have worker 0, 1, 2 ready, controller 0, 1, 2 also ready, and all of them running with unique IP addresses available. Next one, these are not static IPs, by the way. These are not static. They're just temporary transient IPs assigned to those machines. Next one, we'll now begin the grunt work. This is really grunt. I'm just cautioning you. There is too much thing to do with certificate generation because everything in Kubernetes these days is TLS authenticated. And so you have to have a certificate authority in place, and you will see the motions as we go along, but you're now in that stage where the grunt starts. It can be a little bit of grunt for those of you who are not super familiar with command line, or those of you who don't want to do this. As you know already, you don't have to do this, honestly. But just watching is fun when other people are going through grunt. So watch me go through the grunt. Let's put it that way. You're welcome to do that, by the way, because you will actually understand what security, TLS, and certificate authority, these things are. I'll explain it to you as I do it. So here we go, provisioning a CA. So what we are really creating is creating a method for us to issue certificates to other machines and other machine-to-machine communication. We'll use this toolkit called CFSSL, which is provided to us from Cloudflare company, who has created a CFSSL binary. This library is also available in open source. That's the library we are using. We already have installed. It's the Cloudflare SpeakAI toolkit. We'll be using that library already. for which we'll create a certificate authority ourselves. We generate TLS certificates for these components. So we'll have new components that will use communication across between services, and every communication is encrypted using these TLS certificates. So we will have certificates for etcd, Kube API server, kubelet, and kube proxy. These are components inside Kubernetes that need that certificate. So we need to have a certificate authority. So we'll create a certificate authority configuration file, and the copy paste beautifully works in this, by the way. So what you do in this copy is you are creating this particular file that contains this content right there. And between the EOF and this EOF, you will see that this caconfig.json contains this content. So right now in our virtual machine, you will find that we don't have that file called caconfig.json, but now we will create this. So before you proceed any further, it will be a good idea to just create a temporary folder. Let's call it Kubernetes the hard way, KTHW, and we'll go inside KTHW and then play inside this folder. So it is currently empty, which is a nice thing to begin with. So we can collect all these resources in one folder. That's why I am creating this folder and I'm going inside that folder to play. Otherwise, you will sprinkle your certificates and this and that all over the machine. Not a good idea. I mean, it's okay to do it, but just make it convenient to put everything in one box, one folder. That's what I'm doing right now, is I'm creating a certificate authority configuration like that. And so now I have that configuration right there. I will use that certificate authorities. Next step is to create a signing request. So this signing request will generate another file like that. So this is the certificate authority signing request CSR JSON. And now I will use these two files to create a certificate and a private key. That is simple to do. Now that we have our CFSSL tool library available, we now have it created. You can see that a certificate sign request was already used, and we now have a private key and this certificate authority created. So these two files are the ones that are going to be useful. ca.key.pem is the private key, and ca.pem is the certificate authority now available. We'll now create admin client certificate. So too many moving parts. I think it's a good idea to speed up a little bit. Otherwise, I will not be able to finish before time. So I'm speeding up. We have about 40 minutes left. So I'm speeding up a little bit. If you want me to slow down, please ask me to do so and ask me to explain if I miss something. So copying a little faster and creating another file. This file is the admin client certificate signing request. And now I will generate the admin client certificate and private key. So it is doing that, and it did that. You can see that it created those things for administrator. So admin key and PEM created. Now I will, create kubectf client certificates. This is the command line that you run on your local computers to configure and interact with the Kubernetes cluster. And that uses this node authorizer, which basically an API request to connect to the cluster, for which we need to have, for every worker node, we need to have a certificate, which requires this step. Yeah, I think I need to go step by step. So we'll copy one portion. I think no, break. No, this is not, you have to copy the whole thing because it's a for loop. So there's a do and an end at the end, there's a done at the end. So you have to copy the whole thing one shot and then run it. Otherwise it will not work. So I copy the whole thing like this and done. Then it will create those certificates and operate and produce a result for worker 0, worker 1, worker 2. And we will have, as a consequence, we will have a result available for us. So we have worker 0, 1, 2, CSR and PEM for those guys. Client certificates available. Next, we'll create kube proxy client certificates. This involves creation of a kube proxy client CSR JSON, which is a cert signing request. which we just created. We'll then use that to generate certificate and private key for this kube proxy, which generates. You can see it. This is your proxy PEM and the certificate authority for that. Next one, we'll create Kubernetes API server certificates. There are too many moving parts. Maybe that's the reason why he calls it the hard way. So there are too many moving parts that we have to really understand each and every piece as we go along. In this step, what we are doing is grabbing public addresses for the Google Cloud Compute addresses described the hard way. And what we are doing is grabbing the public addresses, putting that in a temporary environment variable, and then using that variable, creating another signing request, and then generating another private key and certificate for that. Then we have a Kubernetes key and a Kubernetes PEM also available right there. Kubernetes key and Kubernetes PEM, those guys. Now we need to distribute these client and server certificates. So what we need to do is basically use SCP, this secure copy method, SCP method, to copy our ca.pem files, these files, onto the worker machines. So what I will do is, for instance, in worker 012, copy these guys from our machine and SCP them onto worker 012, like that. So what this will do is send the certificates from here to there. Now it says your public SSH. Here it says warning: the public SSH key file for gcloud doesn't exist.
That run right?
Sorry, again.
It's looking for gcloud's a command, right? But it looks like it's taking it as a parameter.
So I did not understand your question.
That error message you just sent there, those warnings for gcloud.
Mm-hmm. Are you talking about my error message? This is not an error. Mine is not an error.
But you like those warning messages?
No, these warnings are basically indicative of the fact that I did not have a public-private key pair.
For gcloud.
Correct. For the gcloud command, we'll need a separate private public key pair, which is going to be created right now. So it is asking, hey, do you want to use a passphrase? And I said, no. So no passphrase. So empty passphrase again, and it's done.
Okay.
So it generated a new public-private key pair by this name, like the pub key and the private key in the .ssh folder in the home user location. So it is creating that private key, public key for me because I did not have it to begin with, and then pushing those details through the SCP method right there and sending our keys to the workers 0, 1, 2, and that's what's going on and finished. So there was no error as such, except that I did not have this private key, public key already because this is the first time I'm using. So it created for me. That was not an error. It's a warning that you don't have it already. So I'll create it for you. So I said generating public-private key pair for you. You want to use a passphrase? And I said no. That was it. Next, we'll do the same thing this time for the controllers. So we'll say, you know what? Hey, controllers, I have certificates for you. Please take them. So this time it will not prompt me for this public-private key because I already have it. And it just uses the key pair and just sends the keys, the certificates, and the certificate authority over to the controllers also. That's what's going on right now. So we finish that portion. Now we will generate the next step, which is generating Kubernetes configuration files for authentication. That's the next step. We'll proceed forward. And here, what we are doing is to first of all get the static IP of the machine that we have over there, or the collection that we have there. We have a static IP allocated. We'll grab that, put that in this variable, and that is what is assigned to this environment variable right now. And then I will use that reference to construct Kubernetes configuration file, which basically generates for each worker node and that requires this step. So you can see that it is creating this Kubernetes configuration in the default context for all the worker 0, 1, and 2 that finished that action like we asked for here. Next one we are doing is to set up kubeproxy configuration file, which involves creating a kubeproxy kubeconfig file for the kubeproxy service, which are these steps. So kubeconfig set, this is using the kubectl command, by the way, which we have already installed. If you notice the very first step, initial steps, we have this already installed. Yes. So that is what we'll be using to connect to the cluster and send, or rather set this configuration using that CA authority and using embedded servers. And the server that we'll be using is the IP address, the public IP address at that particular port. We are configuring that to use the public IP address that we grabbed in the previous step here. Same thing again for other steps. And the last one, actually it's a never-ending game, so it's not the last one. It'll keep on going like that for about 10 minutes more until we get to the end game, which is when we will see the cluster functional. So the last step here is to use context default. That switched to the default context. Now we need to distribute Kubernetes configuration files. So we'll copy these files that we have locally and send it to the workers. So we'll grab an command, paste it, and it will copy the kube configuration and push it out to worker 0, 1, 2 using the SCP command. That's what you're looking at. And we finished copying. Now we need to generate data encryption, configuration, and key. Now what we want to do is, first of all, generate an encryption key. The encryption key generation is this step. So we already have an encryption key at hand. What we are doing is generating a random number and encoding it to base 64. That's the encryption key I will be using. I will use that encryption key to create a YAML file. The YAML file that you look at will be called encryption config. That file is now created. We'll cat it and see how it looks like. And this is your secret stored right there. This was generated in this step. So this YAML file was created as a consequence of this step. We'll now copy this YAML configuration to all the 3 controllers. So it goes there. Next, we'll bootstrap the etcd cluster. The etcd cluster requires us to, first of all, directly connect to the controller 0. So we'll connect there through SSH command. We are now on the controller 0, on the remote machine number 0. Now in there, we will download etcd binary. etcd is a CoreOS product, open source, and that is what we'll be using. So we'll use that download step. It also has this show progress line in there, which is okay because that machine we are using is not our workstation, but that remote computer called controller 0. So it will work out just fine. You can see the progress right there. This show progress is okay at this time. Next, we'll unzip the tarball on that remote location, which we have etcd downloaded, this tarball. And by the way, you will notice that it has the CA PEM, the CA key PEM, encryption configuration, Kubernetes key PEM, Kubernetes PEM. Those PEM files are loaded up from our machine to that machine already. And we have done it for all the 6 machines we have, 3 workers and 3 controllers. What I will now do is unzip the tarball, rather untar the tarball, and then move that particular collection of folders in etcd into user local bin. So this entire folder that we have, I want to move it to user local bin. So I did that. And now I have that folder inside here called etcd already relocated. Now what I want to do is create a directory to run HCD server, and then copy those PEM files that we have in our home location in the remote machine into the HCD location. Then we want to grab the internal IP address of that machine right there. So we'll grab that using an internal IP by curling the instance itself. So the network interface for interface number 0, get the IP address for that machine. So we're grabbing the internal IP, put that in an environment variable there. Then we will assign HCD name as a unique host name. So that's another variable that we are setting up. Then we'll create an HCD service. This service will be running on that remote controller 0 machine to begin with. And we'll add 2 more to get the entire fault tolerant, reliable HCD service that will be a component inside our Kubernetes cluster, which will be acting as our 3 controllers managing the cluster itself. Then we'll start the HCD server. Right there, it should start. Then we'll systemctl daemon reload, and then enable HCD, and then sudo systemctl start HCD. And then these are the same commands we have to repeat on controller 1 and controller 2. So just get ready for that. I'm currently on controller 0. I want to do the same steps 2 more times on 2 different machines. So I'm coming out of this and then going to the other machines. So I come out, I go to the controller number 1 now and connected. Now I'll go back to the top and I'm connected to controller number 1. And I think I need to speed up because this is a manual step. So I'm, without explanation, going ahead and finishing it off as quickly as I can, because it's quite boring actually if you think about that action. It can be boring. It is boring, no doubt about it. It is boring. But what I'm really doing here essentially is to set up HCD on the 3 controller machines that we have without missing a step. What this will do is make the 3 controller machines act together as a group of managers that will elect. It's basically an odd number of machines by definition. You have to have an odd number of machines in place to make sure that one of them is able to vote and actually win an election in case there is a conflict. Or it's a democracy, by the way. It's a democracy of managers. That's why you have either 1 or 3 or 5 types of setups. In our example, we are now running with 3 machines so that they can vote properly and make sure that the winning argument actually is the correct argument in this setup. That's how the thinking is under the hood behind the idea of having 3 or 5 or an odd number of machines running your management infrastructure. So I just finished the controller number 1. Now we will come out of this, go to the other machine and finish that boring step one more time. So here we go, download our HCD binaries from here. We'll unzip them. And thank goodness I connected to the remote machine using my Macintosh command line, because otherwise I would have been dead by now, just copying and pasting. Yeah. But that's what you need to understand, these steps as to what is going on under the hood and then automate it. So the reason we do the hard way is to really understand how to automate, and then we can actually automate all these steps. There are tools that are available. We have another exercise that will use Terraform and just run it, and it just gives you a Kubernetes cluster. But it will do all these things for you. So I have it already. I'll give you a link of that also, like I mentioned at the beginning. But before I forget, just let it finish. And I don't want to miss any step here. I think this is boring, honestly. If you find it boring and if you want me to stop, you should tell me, because I can do something else, like another exercise that is slightly more interesting than this one. It is already getting boring to me, and I'm pretty sure.
You're almost done anyway.
I know, but there'll be 3 workers also. So that's the problem. That's the problem. So we have 3 controllers and 3 workers. Now we come out of this guy, and then let's see the verification step. So we have etcd API member list. Was it? I think I should still be there on that machine. And no, hold on. I need to be in that remote machine, and there where I need to run this last step. And so yes, they are started, and now I can come out of that controller machines. I came out quickly, a little bit before I was supposed to. Now I can see that they're all started, and they're all running etcd just fine. Next, I'll go bootstrap the control plane. Now we have to be on the controller 0. So we'll go back to controller 0. And then in there, we'll provision the Kubernetes binary. So this is the time when we're actually downloading Kubernetes binaries from the official storage. So this is 190. So I'm bringing down those binaries. They're coming down, and then I will install them like that. And then I will move them in the right location. And then I will configure the API server. And then move the certificates and PEM files and all of that in the var-lib Kubernetes folder. So it moved. Then I will get an internal IP address. Come on, copy please. And then I will create a API service. And then I create a controller manager service. And then I create a system scheduler, kube scheduler service. So multiple services. Then I start the controller services by first of all moving them to the right location in the etcd systemd system folder. Then sudo systemctl daemon reload, and then enable the services, and then start them. And so allow up to 10 seconds for these services to catch up. That's what it tells me. So 10 seconds, I'll count 10 seconds, 1, 2, 3, 4, I think it is 10. So let's go check. And it is healthy. So we have controller manager healthy, scheduler healthy, and etcd 0, 1, 2 all healthy. Now we have to do the same thing on 2 more machines. That's the boring part, but we still have time. So bottom line is, let me go speed up even further if I can. So for which I have to shut up, which is hard. Shutting up is the hardest part. So let's quit. Go to the other machines. And now download Kubernetes binaries. Then you install them. And then you move them to the right folder. Sorry, copy this thing and move to the right location. Then you create an API server. You have to copy all the PEM files into that Kubernetes folder. Then you get an internal IP like that. Okay, come on, my mouse, go faster. And then we start creating services. So systemd unit files for one, for API service. Then the controller manager service. And then the scheduler service. And then we start controller services. So first one, reload, enable, and then start. And then Component status. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not able to connect. Did you go early? I think so. I was too early. We have to wait for 10 seconds before the things become healthy, and now it's healthy. So we'll come out of here and go to the third machine. Now, in the third machine, we'll have to repeat these steps, beginning from download Kubernetes. Then this is getting boring. But I'll do it, don't worry. Unless you get bored, in which case you need to tell me that I should stop.
We need to see it through now.
I'll complete. I have no problem. I'm not in a hurry to go. I will complete the whole thing and you will see it running. No worries about that. But just don't want you to get bored. That's the only concern I have. I never get bored with these things. No, I have no problem. All my real concern is to not bore you. So if you get bored, please tell me. But this is actually one of the most boring exercises. It is actually also interesting at the same time because it's one of the latest. Hold on. Did I forget or creating something or what? Or maybe copy paste.
Just missed the S/.
Aha. Thank you, Travis. By the way, if any one of you has already done this exercise ever before, like Travis, for example, please tell me. Did you do it?
No, I actually haven't done this one yet.
Haven't yet. Okay. So maybe, yeah, you're looking at it happening and you should do it.
Well,
what this will do is give you the ability to run a Kubernetes cluster for somebody, like your company, for example. That's what it gives you a clarity of understanding as to what does it really take to build one from scratch. And what did I just type? Service.
Yeah, I didn't realize all of this gets run through systemd services.
Yeah.
I thought a lot of this would be Dockerized.
Yeah, but this is the hard way approach, right? So that's why.
Okay.
This is the hard way approach. There are easier way approaches that you know a Terraform exercise we ran the last time, if you remember, Travis. That's the exercise I will be running also, which builds up a Kubernetes cluster like in 10 minutes and you're done.
Yeah.
If you can find a link to that GitHub and post it on Slack chat, that will help other people. So if you know what that exercise is from the last time, you build a Kubernetes cluster using Terraform. If you find a link on GitHub, paste it on Slack chat, if you will, please.
Sure. Yeah, I remember one of the guys I met at a meetup had one that he did with Terraform. I'm sure there's a couple. Yeah, let me see what I can find.
Find one that I know works. That's the one. Don't give a random link, right? So
yeah, sure.
Find the one that either you or me know that works.
I'll send it through the pipeline.
Thank you. And so the component status is okay for all these three machines. So we should be able to come out from here and then set up role-based access control for kubelet authorization. So here we have to go back to now machine number 0. And there we will set up role-based authorization, role-based access control. So on the machine 0, controller 0, we just set up another YAML file. And in there, we will now bind this to the Kubernetes user. This role-based access control is fairly complex and absolutely useful. People call it the RBAC rat hole. It can be a rat hole, but it is actually beautifully done if you understand what this is, which is allowing access to people in your company based on their role in the organization. You can also tie it to Active Directory in your company if you have Active Directory, like most companies do. And so based on that, it becomes easy to control access to who can access what, when, and how. So I think we just finished those steps. Let's go set up front-end load balancer. So we have to create a load balancer like that. I think I should come back from here. I should not be on the controller 0, I suspect. In this section, it will provide external load balancer. So I need to come out of it, I think. like that. And back into my machine, I need to set up a target pool. And it did. Then I will create, add the 3 instances to the target pool. Then grab its public facing IP address and set up a forwarding rule to allow inbound traffic according to the firewall rule we have in place, which maps to this port. Then we verification steps. So verify, retrieve the static IP address. Let this finish before I run forward. It is going to create a forwarding rule to allow inbound public access. Then we will identify the public IP address, make an HTTP request to that public IP address. And there we go. So it is showing us a response that it is currently running 190 on that IP address at that port with this version number, because we passed along our certificate authority PEM file. So it responded back successfully. Next, we'll bootstrap worker nodes, which is another boring step. So now we'll do the worker steps. Worker nodes. So here we go. We have to set up our worker machines. So connect to the worker 0. We are connected to the worker number 0. There we install a library called SOCAT. And once this gets installed, we'll use this SOCAT binary to enable port forwarding. That's where it's used, the SOCAT thing. So we'll now install worker binaries. So the worker binaries are also available from Kubernetes. So we'll grab them and then create installation directories for these things to sit. And the directories are created. Now we'll install the binaries in the right folder. So we'll go untar them, like expand the tarball into the right folders. We have downloaded a bunch of things. We are expanding the tarball for plugins and cry container D and kubectl, kubeproxy, kubelet. We are modifying them, making them executable and moving them to the local bin folder. Then we create CNI networking, choosing the pod CIDR that we have already called out. Then we'll create a bridge network. We'll now use the local loopback network configuration. For local loopback, we'll move these files to the etc CNI netd folder. We'll now configure kubelet and move that file into kubeconfig. We'll also move our certificates to the var lib Kubernetes folder. Come on, copy. The certificates copied. Then we create a kubelet systemd unit file like that. And then we configure the kubeproxy like this. Then we create a kubeproxy service. And then we start worker services. And then we reload the daemon. And then we enable and start the kubeproxy and kubelet. Started. Good. Now we can verify this after 10 seconds. Oh, we have to go repeat for 1 and 2 also. So let's go do that. So we'll come out of here, go to number 1, worker number 1, and go to the top. And do it again. 2 more times, and then it's a charm. It's a charm. So we have time. We have 10 minutes. So we should be able to finish it. So installing SOCAT. Doing the binaries, grabbing them from the distribution. We'll create directories for these items to stay in the right location. So we're waiting for the download to finish. And then we create folders. Then we'll install the binaries in the right location. Then we configure our CNI networking on this pod CIDR address space. Then we create a bridge network and a local network. First the bridge one, then a local loopback network, and then you move them to the CNI netd folder. And then you configure kubelet. Move the PEM file to the right location, and establish a kubelet service. And then you configure kubeproxy and another systemd unit. And you start the services, reload, and enable, and start. Then you do the same thing for worker number 2. There we go. Go to the top, install Socat. Then we install these binaries from Kubernetes distribution. Then we'll create folder for them. I need to finish before time. I think I'll do that. Okay. This is the most boring exercise for most people. I have observed this, that it, is just too much. I guess that is true. It is too much. But I think we'll move on to some interesting use cases of using the.
Thinking about this being boring, I've been thinking about how people learn and stuff. And when you're in any kind of martial arts, repetitiveness builds muscle memory and eventually understanding. So that's what we're actually doing here, is trying to build muscle memory and understanding of what the automation is going to do for us, is what you're saying, basically.
Correct.
So the thing I would be doing is I would be actually trying to understand each of these commands and what the options are.
That is the real learning, right? That's where the real learning, that's the rubber meet the road aspect, because that's when you really understand how automation works. Because, just using automation is no good. I can give you, like, I think Travis just posted some exercise. You can get a Kubernetes cluster up and running on a bunch of nodes on, running some command. And so it's fairly trivial. But running that thing alone is not good enough. Understanding and then running thing is much better. That's the hard part. That's also the boring part sometimes. But I think I just finished the worker number 2. So we come out of here, and then we go to controller number 0. And then we'll say, okay, are we ready with the Kubernetes cluster? Are we ready? Let's go check. I am on Kubernetes cluster, and can I see my nodes, please? Apparently so. I am connected and I am correctly configured. So my cluster is up and running, by the way. I will now configure remote access to the cluster. That cluster I have, it runs here. These machines are running right there. There's controller 1012, worker 012. Those machines are running in form of a Kubernetes cluster that I just finished setting up by hand. What I want to now do is not bother too much about going to that controller 0 machine, but I want to operate on it right here from my workstation. So I need to configure remote access. I will use the kubectl command to connect to the remote computer, for which I need to grab a set of credentials that I can put in locally on this machine and then connect to my cluster. What I'll do is, you will generate a kubeconfig file for the kubectl command line utility based on the admin user, which you already have. So what I want to do is run these commands on the same directory used to generate the admin client certificates. So you can see that I need to come out of here and go to this folder where I have the admin client certificates and the PEM and the key. That folder needs to run this exercise, the remainder of the exercise. I think we're almost there to the end. So what we'll do is grab the public IP address first, and then set the configuration for kube control to use the Kubernetes hardware cluster. This cluster I'm setting as my configuration. So it did. Then what I will do is use my admin PEM and local, these administration key and PEM files that I have. I'm going to use those in access to that remote cluster. And then I will define my kubectl context as that cluster. And then I will use that context pretty much like this. And then I have my current computer, this one, local workstation. I have my Linux workstation connected to the remote location already. So I can just operate on that command line just like that. And I can see the same results that I would otherwise see if I am right on those machines out there. I can now run here kubectl get nodes. And I get my nodes like that. Because nodes are the main vehicles that will run your application. So now we can configure pod network routes. We can specify that we would like to get. So there are apparently many other ways to implement this networking model. This is just one of the ways. The ways that we are going to do is what they are describing here is to have the worker 0, 1, and 2 use these routes that we have already configured and called out. These IP address ranges are already called out. We'll be using them and creating a route, network route for each one of them. So that's what I'm currently doing and finishing off through. And then I will list my routes. As soon as this creation of routes happens and gives you the next hop to go as we define it in our creation of those routes, the 0, 1, and 3, the 3-part process, I will see the result coming up right there. We can also deploy DNS add-ons as a next step, but the cluster is up and running and we can remotely connect to it and operate on it and put our YAML deployments and put our services deployments, put our ingress constructions, all of those things we can do basically right from this Linux workstation, because it is now connected through appropriate credentials that we have crafted ourselves and put that in the right places in those 6 machines that we have out there. And as soon as this command finishes, we have practically done completely setting up our cluster as such. Other things that remain to be done are actually never ending, because you have to get an application, configure DNS, and here is the route list that we now know already exists, and we can know how to go wherever we want to go in that cluster as we go along. So those steps finished. Next parts that are described here are the DNS add-on. This DNS add-on is an important thing to have, no doubt about it. But let's go see where it actually belongs in the entire sequence of flow that we have. It is right at that very last stage. So I want to finish that, and then we can do a smoke test and clean up. So we'll do the deploy cluster. The last three pieces, just finishing it off. What I'm doing is setting up kubedns cluster add-on, which requires us to create something using the kubedns YAML, and I'm using kubectl to create a resource in the cluster. So what I'm doing is essentially is kubectl create using this file reference. That file actually creates a service account, creates a config map, and also creates a deployment. So 4 pieces in that YAML file. You can read that YAML file right in that IP address, in that DNS URL. This is the YAML file that just downloaded. You can also download. What did I do? Hold on. You can also download and inspect it. I should not download actually. It should just show in the browser as a YAML file, but apparently no. Looks like it's downloading it for some reason. But I have these service account, config map, service deployment created.
You have
Now
to set your meta type for
exactly.
YAML as a text file.
Yeah, correct. So it is not exposing in the browser, but we'll figure it later. But that's not the issue. The next point I want to go is list all the pods that are currently running in my cluster. So I can see that I have a pod running right there. This pod is running kubedns service that you can see. I can see get pods in the kube system namespace. So I got that result back. Then we will verify. We'll create a BusyBox deployment. So it's a BusyBox is a simple Linux image. I want to run that image and I want to let it sleep in a deployment. So I'm basically creating a deployment like this, kubectl run BusyBox image by the name BusyBox. And this is the command I want to run inside that container. The command is sleep, just sleep for some time. So when you now say, give me the list of pods running, it'll give you the list of BusyBox pods doing nothing but running sleep. And it'll finish sleeping in 3600 seconds, and then it'll finish it off. But that's what you're looking at right now, that pod that we just created a deployment, and it is running currently. It is doing nothing much but sleep. Then we'll retrieve the full name of that BusyBox pod by going it that way, which exported that name in the pod name in the environment name, and then I want to connect to that pod. So I'll say connect directly to that pod by that pod name. So now, and then do an NS lookup on Kubernetes inside that pod. So I'm saying kubectl exec is like docker exec. If you remember docker exec, same idea here. You can connect to a pod by its name. So kubectl exec is like docker exec. Connect to the pod, NS lookup the name Kubernetes, and it comes back with the server and address. Those two addresses show up. That's what you are expected. And then we do a smoke test. Now in the smoke test, what we're doing is generating a secret. So we'll generate. The secret is generated and is stored. It is stored in a remote Kubernetes location. So that's what we did. kubectl create get secrets. You can see the secret is there in the Kubernetes controller. This secret was just created, the hard way secret. That was the name we chose for the secret. It is now available and opaque and in that location. We can actually see the Kubernetes proxy also. Let's see if I can run the proxy. kubectl proxy should show up. The proxy, yes, it is running. So let's go see if we can see the visual interpretation of the cluster, visual display of the cluster in the web browser in our local Linux machine. I am opening my Firefox browser and expecting to see localhost :8001 showing me /UI, showing me my Kubernetes UI dashboard is not installed. Apparently 4 is 404. So I think I have dashboard not installed, which means I need to install a dashboard YAML file, and then the dashboard will expose itself. So apparently that piece is still not there in this step, not included yet. So that's why we don't see the dashboard. But having said, we can proceed further with the remainder of the step, which is we have created a secret. We'll now print a hex dump of the secret stored, which is there. So we see the hex dump coming out. That's the dump. Then we will see that this deployment that we have created before, we'll create another deployment. So run nginx image. So it runs. We can see kubectl, kubectl get pods. Will show us the Nginx container currently creating, and it will soon be running. Then we can say that get pods, which I think I already typed by hand, but I'll copy and paste from here, which will show you the same pod. Now it's running. It was creating before. Then we'll say port forwarding. We can set some port forwarding rules like we have in our cluster, and forward that port from 8080 to port number 80. So that's forwarding setup already. And what I will now do is in a new terminal, meaning in a new terminal like this. Come on, connect to the Cloud Genius workstation. In a new terminal, I would like to now see if I can curl the head. And what do you see? You see Nginx coming up. This is coming straight from the Kubernetes cluster itself, because we have done a port forwarding right there. This forwarding rule is forwarding from the pod, port number 8080 to the port number 80. So when we curl for that port, we see the output coming from Nginx. And we are looking at the head right now. Then we can also switch back and stop the Nginx pod. So switch back to the previous terminal, meaning not this one, but the other one. And in there, we will say that we will break that port forwarding like this, Control C, and then inspect our logs. So we can print our kubectl Nginx logs, if you will, and you will find that there was an access from curl on that time, and it was accessing the head, and it was a 200 OK. So we saw that it successfully reported that somebody actually attempted to access the Nginx container running in that pod. We can also enter that container itself. We'll go inside the Nginx container, and you can see that when we say Nginx-v, we get the Nginx version running inside that container showing up. We can also see other services, like expose our services on a node port. So we expose that particular Nginx container on a node port, and as a consequence of this, what we'll do is grab that node port itself and assign it to a local variable, and then we'll grab the external IP address, assign it to that variable, and then make an HTTP request to that particular node port on that particular external IP, and we'll still see the same thing, which is curl interfacing with that particular external IP on that particular node port on which we exposed, and it is stuck. It should respond back right now. It is not responding. And why it is not responding is probably because our this exposure is not complete yet. It is showing complete, but I'll have to debug as to why this particular piece is not responding the way I expected. When I say curl and a given HTTP IP address and port number, I should see something like 200 OK. That did not happen. But apart from this, every single thing worked just like we expected. So now we will clean up. Cleanup is fairly simple. Just destroy the machines, then you're done. So I will do that. And you also have to clean up the nodes and the IP addresses and port forwarding rules and static IP allocation. You have to go clean up every single thing. If you leave them alone there, it will be causing you a bill. So remember to clean up properly. If you're doing this exercise a couple of times, you clean up. If you don't clean up, your $300 credit will disappear sooner than you expect. And then you will see a charge on your credit card, which is not what you want. So with that, I will stop recording and open for questions. I'll clean up later on, by the way. Cleanup is fairly easy. Just go clean, delete everything. That's what cleanup is. So questions are welcome.